Across the enormous universe, billions of galaxies stretch out in every direction. Each galaxy is filled with countless stars, planets, and strange phenomena, huge groups of stars, massive clouds of gas, and powerful areas where new stars are born far beyond anything we have ever seen. Exploring all of them would be humanity's greatest adventure, a journey not just through space, but through time itself. From the heart of the Milky Way to the farthest corners of space, this journey would uncover the shape, growth, and secrets of every galaxy. Before we begin, let us know in the comments below where in the world you're watching and what the time is there now. Then, settle in for a relaxing journey to the galaxies in our universe. The Andromeda Galaxy is one of the most interesting and beautiful sights in the night sky. It is a barred spiral galaxy, meaning its spiral arms reach out gracefully from a bright, bar-shaped centre, and it is the nearest big galaxy to our own Milky Way. Long ago, before astronomers knew what galaxies really were, Andromeda was called the Andromeda Nebula. Today, it is officially listed in several space catalogues as Messier 31 and NGC 224. This huge galaxy has a very large width of about 152,000 light-years, almost twice the size of the Milky Way, which makes it the biggest member of our cosmic neighbourhood, called the Local Group of Galaxies. It lies at a great distance of about 2.5 million light-years from Earth, or around 765,000 parsecs in space terms. To make that easier to imagine, the light you see from Andromeda tonight actually began travelling toward us about 2.5 million years ago, back when early humans on Earth were first learning how to shape simple stone tools. The name Andromeda comes from the part of the night sky where it appears, the constellation Andromeda, named after a princess from old Greek stories who was saved by the hero Perseus. So, this galaxy carries not only a scientific name but also a mythical one, linking the stars to some of the oldest tales told by people. In terms of total weight, the Andromeda Galaxy is about the same as the Milky Way. Each is thought to weigh around 1 trillion times more than our Sun, an almost unimaginable amount of about 2 times 10 to the power of 42 kilograms. For a long time, scientists believed that Andromeda was much heavier than the Milky Way, maybe by 25 to 50%. But more careful studies in the early 21st century showed that the two galaxies may be much closer in weight than once believed, and in fact, the Milky Way might even be the heavier one. Astronomers also know that these two giant galaxies are not standing still. They are slowly being pulled toward each other by gravity. In about 10 billion years, they are expected to crash together and become one huge new galaxy, possibly forming a bright, round, elliptical or a smooth lens-shaped galaxy. This future cosmic meeting will completely change our night sky, though by that time, our Sun will likely have become a red giant, and Earth as we know it may no longer exist. Even now, Andromeda is one of the brightest deep sky objects we can see from Earth. With an apparent brightness of about 3.5, it can be seen without any telescope on a clear, dark night, even from places with some light pollution. To the naked eye, it looks like a soft, misty patch of light, a ghostly glow stretching across the darkness. Ancient people may have noticed it long before telescopes were invented. Some historians even think that the ancient Babylonians might have written down Andromeda as part of a constellation they called the Rainbow of the Sky. The first clear written record of Andromeda comes from the Persian astronomer Abd al-Rahman al-Sufi, who, around the year 964, described it in his Book of Fixed Stars as a small cloud, or faint smear. This was more than 1,000 years ago, and it remains the oldest known record of a galaxy other than the Milky Way. For hundreds of years after that, astronomers called it the Little Cloud. In the early 17th century, in the year 1612, the German astronomer Simon Marius gave one of the first telescope views of the Andromeda Galaxy. Later, the British astronomer John Flamsteed listed it as 33 Andromedae. In 1745, the French scientist Pierre-Louis Maupertuis suggested a daring idea, that this fuzzy spot of light might actually be an island universe, a faraway system of stars separate from our own. Then, in 1764, Charles Messier added it to his famous list of space objects as M31. Messier mistakenly credited Marius as its discoverer, even though Andromeda had been visible to the naked eye since ancient times. By 1785, the famous astronomer William Herschel noticed that Andromeda's centre had a faint reddish colour. He thought it was the nearest of all the great nebulae, and from its brightness, he guessed it was about 18,000 light-years away, which was wrong, but still an amazing try for his time. In the mid-19th century, in 1850, William Parsons, also known as the third Earl of Rosse, made one of the first drawings showing Andromeda's spiral shape. This was an important step forward in realising that some nebulae were not just clouds of gas, but huge star systems with clear shapes. Then, in 1864, another astronomer, William Huggins, studied Andromeda's light with a spectroscope and found something surprising. Its light pattern did not look like that of a gas cloud, but was more like the mixed light of many stars. This showed that Andromeda was made up of stars, a galaxy, not a nebula. In 1885, a bright new point of light appeared in Andromeda, a supernova, though astronomers at the time called it Nova 1885, because they had not yet learned the difference between novae and supernovae. It was the only supernova ever seen in Andromeda. Then, in 1888, the astronomer Isaac Roberts took one of the first long-exposure photos of Andromeda. His picture showed its spiral shape in amazing detail, though he still thought it was part of the Milky Way, a common mistake back then. By the early 20th century, astronomers began to find clues that changed everything. In 1912, Vesto Slipher used spectroscopy to measure Andromeda's movement. He found that it was moving toward us at an incredible speed of about 300 kilometers per second, faster than any other object ever measured at the time. This started a new understanding of galaxies as separate huge systems spread out across the universe. Interestingly, the thinker Immanuel Kant had already suggested this idea as early as 1755. In his book, Universal Natural History and Theory of the Heavens, he said that the Milky Way was just one of many island universes as galaxies, floating in the wide space. His forward-thinking ideas predicted discoveries that would not be proven for more than 150 years. In 1917, another big discovery came when the American astronomer Heber Curtis studied a nova in Andromeda and found 11 more in older photos. He noticed that these novae were about 10 times dimmer than others seen elsewhere in the sky. From this, he worked out that Andromeda must be about 500,000 light-years away, much farther than the edge of the Milky Way. Although this estimate was still smaller than the real distance, it was close enough to show that Andromeda was not a nearby nebula, but a whole other galaxy. This supported the island universe idea, that the universe is filled with countless galaxies, each shining with its own billions of stars. Andromeda, once thought to be just a cloud in our cosmic neighbourhood, was shown to be another grand spiral galaxy, like our own, moving through the endless dark of space beside us. In the early part of the 20th century, the universe was still full of mysteries, and one of the most famous scientific debates in history took place. In the year 1920, two astronomers, Harlow Shapley and Heber Curtis, argued in what became known as the Great Debate. They discussed passionately the true nature of the Milky Way, the mysterious spiral nebulae seen through telescopes, and the real size of the universe. Curtis supported the bold idea that the Great Andromeda Nebula was not part of our galaxy, but a separate island universe, a galaxy in its own right, lying far beyond the Milky Way. To support his view, he pointed to the dark bands in Andromeda, which looked like the dust clouds in our own galaxy. He also mentioned earlier measurements of Andromeda's Doppler shift, which showed that it was moving like a separate distant system, rather than a nearby gas cloud. Just 2 years later, in 1922, the Estonian astronomer Ernst Öpik came up with a clever way to measure how far away Andromeda was. By studying the motion of its stars, he found that it must be about 450 kiloparsecs away, roughly 1.5 million light-years, placing it far outside the Milky Way. This was a new and amazing idea at the time, suggesting that our galaxy was not the whole universe, but only one among many. Then came Edwin Hubble, who forever changed how we see the universe. In the year 1925, using the giant 100-inch Hooker telescope at Mount Wilson Observatory, he found special stars called Cepheid variables inside Andromeda. These stars brighten and dim in a steady pattern, allowing astronomers to find their true distances. Hubble's photos and careful measurements showed beyond doubt that the Great Andromeda Nebula was not part of our galaxy at all. It was a separate galaxy, millions of light-years away. This discovery ended the Great Debate, and greatly expanded humanity's understanding of the universe. 2 decades later, in 1943, Walter Baade became the first person to clearly see single stars in the centre of the Andromeda Galaxy. With careful study, he found that the stars there belonged to 2 different groups. The younger, hotter, and faster stars in the galaxy's disk he called Type 1, while the older, cooler and redder stars in the centre he called Type 2. This grouping, later used for stars in other galaxies too, helped astronomers realise that galaxies change and grow old just like stars do. Baade also discovered there were 2 kinds of Cepheid variable stars, meaning earlier distance measurements, including those to Andromeda, had been too small. When he fixed the numbers, the distance to Andromeda and the size of the known universe basically doubled overnight. By the middle of the 20th century, new technology allowed astronomers to study galaxies beyond visible light. In 1950, Robert Hanbury Brown and Cyril Hazard at Jodrell Bank Observatory found radio waves from the Andromeda Galaxy for the first time. A few years later, in the 1950s, John Baldwin and his team at the Cambridge Radio Astronomy Group made the first radio maps of Andromeda, showing strong activity invisible to normal telescopes. The galaxy's bright centre became known in the second Cambridge Radio Catalogue as 2C56. Then, in 1959, astronomers André Lallemand, Monsieur Duchenne, and Merle Walker found that the centre of Andromeda was spinning quickly. Using the 120-inch telescope and Lallemand's new electron camera at the Lick Observatory, they estimated that the core had a weight of about 13 million times that of the Sun. Just 2 years later, in 1961, Merle Walker found a similar spinning centre in the small nearby galaxy Messier 32, with a weight close to 10 million suns. These discoveries were early clues that something incredible was hiding at the centres of galaxies, what we now call supermassive black holes, the huge engines that power galaxy centres. As the years went by, new findings kept uncovering Andromeda's hidden secrets. In the year 2009, astronomers noticed a rare event called microlensing, where the light from a faraway object bends because of the gravity of a heavy body passing in front of it. This rare event might have been the first hint of a planet inside the Andromeda Galaxy, a surprising sign that worlds could exist even in other galaxies far beyond ours. In the year 2020, observations made with several large radio telescopes, the Westerbork Synthesis Radio Telescope, the Effelsberg 100-metre radio telescope, and the Very Large Array, revealed something even more amazing. They found that Andromeda's magnetic fields were neatly lined up along a wide 10 kiloparsec ring of gas and starbirth, showing that magnetic forces help shape the galaxy's beautiful spiral look. Only a few years later, in 2023, an unbelievable discovery came not from professional scientists but from a group of dedicated amateur astronomers, Marcel Drexler, Xavier Strotner, and Jan Sainty. They found a huge, faint cloud full of oxygen just south of the Andromeda Galaxy, near the bright star called 35 Andromedae. The cloud, later named SDS-01, was so dim that it took many hours of exposure time to capture its ghostly shine, which seemed to glow only in the light of doubly ionized oxygen. At first, scientists thought SDS-01 might be an object outside the Milky Way, maybe formed by the meeting of the halos of our galaxy and Andromeda's. But later studies using spectroscopy showed that the cloud is actually inside our own galaxy. A recent idea suggests it may be a bull shock, a glowing arc of gas made by the movement of a dying double star system called E.G. Andromedae through nearby interstellar matter. In the year 2025, the National Aeronautics and Space Administration showed one of the most detailed pictures of Andromeda ever made. Using over 600 separate photos taken by the Hubble Space Telescope, over 10 years of careful watching, scientists created a huge mosaic showing hundreds of millions of single stars. Among them, about 200 million were brighter and hotter than our Sun, yet this still makes up only a small part of Andromeda's total number of stars. The result is a breathtaking view into another galaxy, our nearest great neighbour, huge, old, and endlessly mysterious, a reminder of how far human curiosity has taken us into the depths of space. In the middle of the 20th century, our knowledge of the Andromeda Galaxy took a big step forward. In the year 1953, astronomers found a second, dimmer kind of Cepheid variable star. This important discovery doubled the estimated distance between our Milky Way and the Andromeda Galaxy. Later, in the last 10 years of the 20th century, scientists used data from the European Space Agency's Hipparcos satellite to improve these distance measurements even more. By studying both red giant stars and red clump stars, they were able to make the Cepheid distance scale more exact and bring new clarity to our understanding of how far Andromeda really is from us. Billions of years earlier, a huge cosmic event had shaped the Andromeda Galaxy itself. Between about 2 and 3 billion years ago, two large galaxies crashed together in a surprising merger near the area where Andromeda now lies. The two galaxies were not the same size. The bigger one was about 4 times heavier than its partner, but their violent meeting left marks that can still be seen today. The discovery of this ancient crash came from studying Andromeda's stars and noticing something strange. Their ages and movements did not match what would be expected in a calm, steady galaxy. Astronomers found that around 2 billion years ago, starbirth across Andromeda's wide disk had been far more active than it is now, proof of a great disturbance in its past. Through complex computer modelling, scientists rebuilt this galactic crash and learned that it likely formed many of Andromeda's present-day parts. The merger seems to have created the galaxy's metal-rich halo, the giant stellar stream, and both its thick and thin disks. It may even have formed a huge circular ring about 10,000 parsecs from the galaxy's centre. During that violent time, Andromeda's rate of starbirth was so high that it briefly became what astronomers call a bright infrared galaxy, shining strongly in infrared light for about 100 million years. These same models also rebuilt the shape of Andromeda's central bulge, its large bar-shaped structure, and the overall thickness of its outer halo, showing how one ancient collision shaped much of the galaxy we see today. For some time, researchers thought that Andromeda and the smaller Triangulum galaxy, also called Messier 33, might have passed very close to each other between 2 and 4 billion years ago. However, more exact measurements from the Hubble Space Telescope later showed that such a close meeting was unlikely. Finding the true distance from Earth to the Andromeda Galaxy has long been a hard task for astronomers, and over the years, at least 4 different methods have been used. In the early years of the 21st century, new methods brought even better exactness. In the year 2003, scientists used a method called infrared surface brightness changes and adjusted their results for metallicity effects, giving an estimate of about 2,570,000 light-years. The next year, using the usual Cepheid variable method, they got a slightly smaller value of about 2,510,000 light-years. Then, in the year 2005, astronomers made an amazing discovery, a pair of hot blue stars in Andromeda that formed an eclipsing binary system. By carefully measuring how the stars dimmed as they passed in front of each other, scientists could find their exact sizes and brightness. From these values, they figured out the distance to the system to be about 2,520,000 light-years, placing the whole Andromeda Galaxy at roughly the same distance. Another method, called the tip of the red giant branch method, gave a similar result of 2,560,000 light-years. When all these measurements were combined, the average distance to Andromeda was found to be about 2,540,000 light-years from Earth, a distance that modern astronomers still accept with strong trust. For many years, the weight of the Andromeda Galaxy was also a topic of debate. Until the year 2018, most guesses said that the entire halo of Andromeda, including its huge amount of dark matter, was about 1.5 trillion times the mass of our Sun, a bit larger than the Milky Way's estimated 800 billion solar masses. Earlier studies, however, had suggested that both galaxies might actually have very similar masses. Then, in 2018, new radio observations supported this earlier idea, showing that the Milky Way and Andromeda are likely close to equal in total mass, each holding about 800 billion solar masses. Other studies in the early 21st century showed that Andromeda's rounded centre is thicker in stars than that of our own galaxy, and that its star-filled disk stretches to almost twice the width of the Milky Way's disk. The total mass of Andromeda, depending on the method used, is thought to be between 800 billion and a little over 1 trillion solar masses. Of this, between 10 and 15 times 10 billion solar masses are made of stars, with nearly 1/3 of them in the central bulge, a little over half in the galactic disk, and the rest spread throughout the halo. By the year 2019, newer studies based on escape speed and motion measurements placed Andromeda's total mass at about 800 billion solar masses, about half that of the Milky Way, which by then was thought to have a mass of about 1.5 trillion solar masses. Besides its countless stars, the Andromeda Galaxy also holds huge amounts of gas and dust. Its interstellar material contains at least 7 billion solar masses of neutral hydrogen, more than 300 million solar masses of molecular hydrogen within its inner 10,000 parsecs, and about 50 million solar masses of dust. Around the galaxy is a giant halo of hot gas, almost invisible to the eye but incredibly large, stretching nearly 1 million light-years into space, about halfway toward our own galaxy. This enormous halo may hold about half as much mass as all the stars within Andromeda itself. Astronomers believe this halo formed around the same time as the galaxy, filled with heavy elements made in countless supernova blasts. Every time a massive star in Andromeda's disk ended its life in a bright supernova, it threw out elements like carbon, oxygen, and iron far into space, slowly filling the halo with this cosmic material. Over billions of years, nearly half of all the heavy elements ever made by Andromeda's stars have been blown far beyond its visible disk, which stretches about 200,000 light-years across. The Andromeda Galaxy shines with a brightness of about 2 6/10 times 10 to the power of 10 solar luminosities, meaning it gives off about 25% more light than our own Milky Way. However, because it appears at a steep angle when seen from Earth, much of its light is blocked by interstellar dust drifting through its wide spiral arms. This makes it hard for astronomers to know its true brightness exactly. Some scientists think that Andromeda may even be the second brightest galaxy within a region stretching 10 megaparsecs around the Milky Way, outshined only by the smooth Sombrero Galaxy. Its absolute magnitude has been guessed at about -22.21, though different studies have given slightly different results. In the year 2010, observations made using the powerful Spitzer Space Telescope showed that Andromeda's true brightness in the blue part of the visible light range is around -20.89. With a colour index of +0.63, this equals a true visual brightness of about -21.52, compared to roughly -20.9 for the Milky Way. At that wavelength, the total light output of Andromeda was guessed to be about 3 64/100 times 10 to the power of 10 times the Sun's brightness, making it one of the brightest galaxies in our cosmic neighbourhood. Even with its brightness, Andromeda's current rate of star-making is surprisingly small. Each year it creates only about 1 sun's worth of new stars, while the Milky Way forms roughly 3 to 5 sun-sized masses in the same time. Even the rate of novae, star blasts that briefly brighten a galaxy, is about twice as high in our own Milky Way compared to Andromeda. This shows that Andromeda probably went through a great period of heavy star-making long ago, but is now resting in a calmer stage of its life. Meanwhile, our Milky Way keeps shining with more youthful energy, filling its spiral arms with new stars. If this continues, the total brightness of our galaxy might one day pass that of Andromeda itself. Modern studies place the Andromeda Galaxy in what astronomers call the Green Valley on the galaxy colour brightness chart. This area is a middle zone between the blue cloud, which holds galaxies still busy making new stars, and the red sequence, where older galaxies have mostly stopped star-making altogether. Galaxies in the Green Valley, like Andromeda and our own, are slowly running out of the gas and dust needed to form new stars. In computer models of galaxies like Andromeda, star-making is expected to stop completely within about 5 billion years, even after counting the short burst of new star-making that may happen when Andromeda and the Milky Way finally crash and join together. In visible light, Andromeda is listed as an Cesspy galaxy in the de Vaucouleurs-Sandage system, a way astronomers sort spiral galaxies by their shape and build. Yet facts collected from the 2-micron all-sky survey and the Spitzer Space Telescope in the infrared range showed a hidden truth. Andromeda, much like the Milky Way, has a central bar shape. This stretched out bar is turned about 55 degrees to the left from the main disk, shaping the galaxy's smooth spiral pattern. Astronomers have long argued over how to define the exact size of a galaxy, since different measuring methods often give different results. One widely used standard is the D25 isophote, which marks the area where the brightness of the galaxy's blue light drops to 25 magnitudes per square arc second. According to the third reference catalogue of bright galaxies, printed in 1991, Andromeda's D25 width measures about 46 56/100 kiloparsecs, which is roughly 152,000 light-years, at a distance of about 2.5 million light-years from Earth. An earlier guess made in 1981 gave a slightly larger width of 54 kiloparsecs, or about 176,000 light-years. In the year 2005, views from the Keck telescopes showed a faint ghost-like halo of stars around Andromeda, stretching far beyond its bright spiral arms. These stars in the outer halo move in a messy way, unlike those in the galaxy's main disk, which follow more even paths moving at about 200 kilometers per second. This thin halo spreads outward to a width of roughly 67 and 4500ths kiloparsecs, which equals about 220,000 light-years, an enormous ball of dim starlight surrounding the galaxy. From our point of view on Earth, Andromeda looks tilted at an angle of about 77 degrees. If it were tilted to 90 degrees, we would see it perfectly side-on. Detailed study of its build shows that Andromeda's disk is not perfectly flat, but instead has a clear S-shaped bend. Astronomers think this bend might be caused by the pull of nearby smaller galaxies. One possible cause could be the smaller galaxy called Messier 33, whose gravity may be slightly twisting Andromeda's large spiral arms. Through careful light studies, scientists have been able to measure how Andromeda spins at different distances from its bright centre. Near its core, about 1,300 light-years away, the stars move at a speed of roughly 225 kilometers per second. Farther out, at a distance of 7,000 light-years, the speed falls to around 50 kilometers per second, before rising again and reaching a high of 250 kilometers per second at a distance of about 33,000 light-years from the centre. Beyond that, the turning speed slowly drops, falling to about 200 kilometers per second at a distance of 80,000 light-years. These speed patterns show that Andromeda holds a very packed mass, around 6 times 10 to the power of 9 sun masses, within its centre, with total mass growing steadily outward to about 45,000 light-years before spreading more slowly. The spiral arms of the Andromeda Galaxy shine with the light of many H2 regions, huge clouds of hydrogen gas lit up by newborn stars. These bright areas were studied closely by the German-American astronomer Walter Baade, who said they looked like beads on a string. His careful work showed 2 beautiful spiral arms that, though tightly wound, are spaced more widely than those of our Milky Way, giving Andromeda its special smooth shape as it moves across the dark space. The Andromeda Galaxy, seen from Earth at a sharp angle close to side-on, hides much of its true spiral beauty behind its tilt. Because of this, astronomers have found it quite hard to study the exact shape of its spiral arms. However, when scientists used special fixed images to straighten its look, the galaxy showed what seemed to be a fairly normal spiral form. 2 large, trailing arms curl smoothly around its bright centre, each one spaced by at least 13,000 light-years, an amazing gap of about 820 million astronomical units. These arms can be followed outward, starting from roughly 1,600 light-years, or 100 million astronomical units, from the galaxy's shining heart. Still, not everyone agrees on this shape. Some astronomers have said that Andromeda might have only one spiral arm, while others think its arms could be part of a fluffy pattern, a soft, uneven web of long, thick strands rather than smooth, clear curves. Much of the bending in Andromeda's spiral shape is thought to be caused by the pull of its smaller partner galaxies, Messier 32 and Messier 110. This pull can be seen in the strange shift of neutral hydrogen clouds, which seem to move away from the pattern of the galaxy's stars, as if pulled by unseen cosmic hands. In the year 1998, the European Space Agency's Infrared Space Observatory gave a surprising new look at Andromeda. It showed that the galaxy's overall shape might actually be changing, slowly turning into what astronomers call a ring galaxy. Instead of having a smooth spiral shape, its gas and dust seemed to form several overlapping rings. One ring in particular stood out, forming a great circle about 32,000 light-years, or 9.8 kiloparsecs, from the galaxy's bright centre. This huge feature earned a poetic name, the Ring of Fire. Hidden from visible light by cold space dust, this area glows brightly in infrared pictures, showing that it is one of the most active places of star-making in the whole galaxy. Later studies with the National Aeronautics and Space Administration's Spitzer Space Telescope gave an even clearer view. The infrared image showed that Andromeda's spiral shape actually has 2 main arms that wind outward from a central bar and stretch far beyond the large outer ring. Yet these arms are not smooth and unbroken. They look cracked and uneven. as if the galaxy's grand design had been shaken by past meetings. Closer study of Andromeda's inner areas with the same telescope showed a smaller dust ring. Astronomers think this inner ring was made when the small satellite galaxy Messier 32 passed right through Andromeda's disk more than 200 million years ago. Computer models suggest that this crash happened along Andromeda's polar axis and stripped away more than half of Messier 32's mass. The violent event also began the making of the round rings that now shape much of Andromeda's build. The presence of both a large old outer ring and this newly found, smaller inner ring, slightly off-centre from the galaxy's heart, strongly supports the idea that Andromeda once went through a nearly head-on crash with its partner, though less violent than the dramatic meeting that formed the well-known Cartwheel Galaxy. Studies of Andromeda's wide outer halo show that it is much like that of our Milky Way. The stars in this area are mostly old and metal-poor, meaning they have fewer heavy elements than younger stars, and their metal content drops the farther they are from the galaxy's centre. This likeness between Andromeda and the Milky Way shows that the two galaxies have grown along similar paths, each growing by taking in smaller galaxies. It is believed that both have joined with or swallowed between 100 and 200 small galaxies over the past 12 billion years. The halos of both galaxies stretch so far that the outermost stars may reach nearly 1/3 of the space between the Milky Way and Andromeda themselves, a huge unseen bridge of ancient starlight. At the very centre of the Andromeda Galaxy lies a thick, tightly packed group of stars, very much like the one found in the middle of our Milky Way. When seen through a large telescope, this bright central area looks like a single shining point, surrounded by a soft, misty glow of light. In the year 1991, the Hubble Space Telescope took a clear picture of Andromeda's inner core and showed that it actually has two separate bright spots. These two centres are about 1.5 parsecs, or roughly 5 light-years apart. The brighter spot, called P1, is slightly off to the side, while the dimmer one, called P2, marks the true centre of the galaxy. Inside P2 lies a small, tight group of stars known as P3, filled with bright ultraviolet blue A-type stars, and at its very heart sits the galaxy's supermassive black hole, named Messier 31 star. This huge black hole is a low-brightness active galactic centre, meaning it feeds quietly on nearby matter and gives off mostly radio and X-ray light. It stayed mostly calm between the years 2004 and 2005, but showed strong bursts between 2006 and 2007, and another X-ray flare in the year 2013. Early measurements in 1993 guessed its mass to be between 30 and 50 million times that of our Sun, while later studies in 2005 placed it between 110 million and 230 million solar masses. The gas and dust circling around it move at very high speeds of about 100 miles per second, showing the great pulling power of this hidden giant. Scientists think that Andromeda's strange double core might be caused by a disk of stars moving around the central black hole in stretched or oval paths. In such paths, stars spend more time at their farthest points, making a patch of light that makes one side look brighter. This oval disk may have formed after two black holes crashed long ago, sending out waves of gravity that shook and reshaped the nearby stars into their current paths. Inside P2, there is also a small disk of hot A-type stars that shine strongly in blue and ultraviolet light, making P2 look brighter than P1 when seen through some filters. When this unusual double core was first found, some scientists thought the brighter part might be the leftover of a small galaxy that Andromeda had swallowed. But this idea is no longer agreed upon, because such a core would not have lasted long under the strong pull of Andromeda's central black hole. While it might be possible for P1 to have its own small black hole that helps it stay stable, the way the stars are spread out does not support this. Instead, the twin cores of Andromeda's centre show that it has a far more complicated and interesting past, one shaped by old crashes, gravity movements, and the never-ending pull of the galaxy's central black hole. By the end of the year 1968, scientists still had not found any X-rays coming from the Andromeda Galaxy. Then, on the 20th of October in 1970, a high-altitude balloon test set a limit on how strong any X-rays from Andromeda could be. Many years later, the Swift Burst Alert telescope, during a full-sky survey, finally found hard X-rays coming from a small spot about 6 arc-seconds away from the galaxy's centre. More studies showed that the X-rays with energies above 25 kilo-electron-volts came from a single source called 3XM-M J00423 2.1+4 11314. This source turned out to be a pair of objects, a dense, heavy object, either a neutron star or a black hole, pulling in and eating matter from a nearby star and giving off great amounts of energy in the process. Since then, scientists using the European Space Agency's Space Telescope, XMM Newton, have found many more X-ray sources spread across Andromeda. According to Robin Barnard and his team, these strange objects are likely black holes or neutron stars. As they swallow nearby gas, it becomes so hot, reaching millions of degrees, that it shines brightly in X-rays. The two kinds can be told apart mostly by their masses, with black holes being much heavier. Later, the NuSTAR Space Telescope found 40 of these objects in Andromeda, showing a busy population of small but powerful systems. In the year 2012, scientists saw something even more amazing: a microquasar, a smaller version of a quasar powered by a black hole that gives off strong radio waves. This tiny black hole found near Andromeda's centre had about 10 times the mass of our Sun. It was first seen in data from XMM Newton, and later confirmed by NASA's Swift Gamma-ray Burst mission, the Chandra X-ray Observatory, the Very Large Array, and the Very Long Baseline Array. This was the first time such a microquasar had ever been found, not just in Andromeda but also outside our own Milky Way. Andromeda also has many globular clusters, round, dense groups of old stars. Around 460 of these clusters belong to the Galaxy. The biggest one, called Male 2 or Globular 1, is brighter than every other globular cluster in the whole local group of galaxies. Holding several million stars, it shines about twice as brightly as Omega Centauri, the brightest cluster in the Milky Way. Interestingly, Male 2 has several generations of stars and is too large and complex for a normal cluster, leading scientists to think it might be the leftover centre of a small galaxy that Andromeda swallowed long ago. The brightest cluster seen from Earth is called G76, found along the eastern half of Andromeda's southwestern arm. Another large cluster, 037 B327 or Bol 37, found in 2006, was once thought to be even larger than Male 2, but later studies showed it is similar in size and features instead of greater. Unlike the Milky Way's globular clusters, which are all very old, Andromeda's clusters show a wide range of ages. Some are as ancient as the galaxy itself, while others are much younger, only a few 100 million to about 5 billion years old. In 2005, scientists found a completely new kind of star cluster in Andromeda. These new clusters have hundreds of thousands of stars, like globular clusters in number, but are far bigger, stretching hundreds of light years across. Because of their size, they are also much less dense, with more space between each star. The largest globular cluster in Andromeda, called B023G078, is thought to have a medium-sized black hole at its centre, one that weighs nearly 100,000 times as much as the Sun. In the year 1999, scientists saw an interesting microlensing event in Andromeda, named PA99N2. This event was caused by the bending of light from a faraway red giant star, likely by another star with a mass between 0.02 and 3 6/10 that of the Sun. The data even suggested that this bending star might have a planet about 6 1/3 times the mass of Jupiter. If proven, it would have been the first planet ever found outside our galaxy, an extragalactic planet. However, later studies showed some strange details in the data, making the finding uncertain. Andromeda, much like the Milky Way, has its own group of smaller companion galaxies, more than 20 dwarf galaxies that circle it. The best known are Messier 32, M32, and Messier 110, M110. Evidence shows that M32 once passed very close to Andromeda and may once have been a bigger galaxy before Andromeda tore away its outer parts. This event probably caused a burst of star formation in M32's centre that lasted until quite recently. M110 also seems to be interacting with Andromeda. Scientists have found streams of metal-rich stars in Andromeda's halo that were likely pulled away from these smaller galaxies. M110 has a dark, dusty band that suggests star formation is still going on, or happened not long ago, while M32 has younger stars as well. The Triangulum Galaxy, another close member of our galactic neighbourhood, floats in space about 750,000 light-years away from the Grand Andromeda Galaxy. Astronomers are still not sure whether Triangulum is truly a satellite companion of Andromeda, or simply a nearby neighbour moving on its own path through the universe. In the year 2006, astronomers made an interesting and surprising discovery. They found that 9 of Andromeda's smaller companion galaxies seem to line up in a single, enormous plane that goes right through the centre of Andromeda itself. This strange and neat alignment suggests that these galaxies might share a common past. Perhaps they were all formed together long ago, or were pulled into their present positions by the huge pull of Andromeda's gravity. Andromeda, the large spiral galaxy that is the Milky Way's biggest and most distant neighbour, is slowly but steadily moving toward us at an amazing speed of about 110 kilometres, or roughly 68 miles, every second. When astronomers measure its motion in relation to the Sun, Andromeda appears to be coming even faster, around 300 kilometres, or 190 miles per second. This difference happens because the Sun itself is not still. It is also speeding through space, circling the Milky Way's centre at a very high speed of about 225 kilometres, or 140 miles every second. Because of this movement, Andromeda is one of only about 100 known galaxies whose light is blue-shifted. This means that, as the galaxy moves toward us, its light waves are slightly pressed together, giving them a faint bluish tint when seen through powerful telescopes. Although astronomers have measured its approach quite accurately, they are still less sure about Andromeda's sideways or tangential motion compared to our own galaxy. Most scientists believe this sideways drift is much slower than its forward approach. When astronomers first guessed this sideways motion, they thought that the Andromeda Galaxy and our Milky Way would crash straight into each other in about 4 billion years. Later, with new and more exact data gathered by the Gaia spacecraft, scientists improved their understanding of how nearby galaxies in our local group affect each other through gravity. Their new calculations show that while Andromeda and the Milky Way may still come close enough to interact, the chance of a direct harmful collision is now seen as smaller than once feared. If such a meeting does happen, it would be one of the most amazing events in the history of the universe. The 2 grand spiral galaxies might join into a single, enormous elliptical galaxy, or perhaps create a huge shining disc-shaped system unlike anything astronomers have ever seen. Such galaxy mergers are not rare. They happen quite often in tightly packed galaxy groups spread throughout the universe. Yet, what might happen to Earth and our solar system during such a space meeting is still not known. Some scientists think that before the final merger, the strong pull of gravity could throw our solar system out of the Milky Way completely, sending it floating alone through the deep, dark space between galaxies, or perhaps pulling it into the outer edges of the Andromeda Galaxy itself. From our planet, the Andromeda Galaxy holds a special place in the night sky. It is one of the farthest objects that can be seen with the naked human eye, a faint misty patch of light hanging softly in the darkness. Only a few other galaxies, such as the Triangulum Galaxy, also called M33, and the Great Spiral Galaxy M81, which can be seen only by those with very sharp eyesight under perfectly dark skies, share this rare honour. The Andromeda Galaxy lies within the constellation of Andromeda, which can be easily found by using the nearby constellations Cassiopeia and Pegasus as guides. Cassiopeia is shaped like a striking W, while Pegasus is known for its large square group of stars. For watchers in the Northern Hemisphere, Andromeda is best seen on clear autumn nights, when it climbs high above the horizon and shines most brightly around midnight in October. As the months go by, it rises earlier in the evening, about 2 hours sooner each month. By September, it can be seen coming up in the eastern sky during early evening, and by February it goes down in the west before midnight. For those living in the southern hemisphere, Andromeda can still be seen between October and December, though it appears lower in the sky and is best seen from places closer to the equator. Even a simple pair of binoculars can show the galaxy's stretched oval shape and its 2 brightest companion galaxies, known as M32 and M110. A small amateur telescope can show even more wonders: the hazy glow of Andromeda's huge spiral disk, dark lanes of space dust, a few sparkling globular clusters, and a great shining star cloud called NGC 206. The Milky Way, often called the Milky Way Galaxy, is the huge island of stars that contains our solar system. Its name comes from how it looks from Earth, a soft, faint band of light stretching across the night sky. This glow is made up of countless distant stars that are so far away we cannot see them one by one with the naked eye. The Milky Way is a barred spiral galaxy, meaning it has spiral arms that spread outward from a bright central bar. It stretches about 87,400 light-years across and is about 1,000 light-years thick in the area of the spiral arms, becoming much thicker near the central bulge. Some computer simulations suggest that its outer parts, which include dark matter and scattered stars, may reach as far as 2 million light-years in width, a size that makes our galaxy truly huge. The Milky Way is not alone in space. It has many smaller companion galaxies, such as the Large and Small Magellanic Clouds, and together they form part of a larger group known as the Local Group. This group belongs to an even bigger structure called the Virgo Supercluster, which itself is part of a very large cosmic network known as the Laniakea Supercluster, a massive region of connected galaxies that stretches across hundreds of millions of light-years. Our galaxy contains between 100 billion and 400 billion stars and possibly a similar number of planets. The solar system lies about 27,000 light-years from the centre of the Milky Way, on the inner edge of one of its spiral arms known as the Orion Arm. Closer to the centre, within about 10,000 light-years, stars gather closely to form a bright bulge. At the very heart of the Milky Way lies a strange and powerful object, Sagittarius A, a very large black hole with a mass about 4 million times that of the Sun. Some of the oldest stars in the Milky Way are nearly as old as the universe itself, having formed not long after the dark ages that followed the Big Bang. These old stars serve as quiet witnesses to the earliest parts of cosmic history. The Milky Way first showed its true nature through the work of Galileo Galilei in the year 1610, when he used his telescope to show that the faint band of light was made up of countless stars. For centuries afterward, astronomers believed the Milky Way contained every star in existence. It was not until the Great Debate of 1920, between Harlow Shapley and Heber Daust Curtis, and the later observations by Edwin Hubble in 1923, that scientists realized the Milky Way is only one of many galaxies scattered throughout the huge universe. When seen from a dark place, the Milky Way appears as a pale, glowing arc about 30 degrees wide stretching across the night sky. Every star that we can see without a telescope belongs to the Milky Way, yet the term Milky Way refers specifically to this bright band of light. Its glow comes from the combined light of countless stars and interstellar dust gathered in the direction of the galactic plane. Some parts of the band shine more brightly and appear as soft patches called star clouds, the largest of which is the Large Sagittarius star cloud, part of the galaxy's central bulge. In contrast, the dark gaps that break the band, such as the Great Rift and the Coalsack Nebula, are caused by thick clouds of interstellar dust that block the light of stars behind them. Peoples of the Southern Hemisphere, including the Inca and the Australian Aboriginals, once saw these dark patches not as empty space, but as dark cloud constellations, shapes formed by the darkness itself. The area of the sky where the Milky Way blocks the view of more distant galaxies is known as the zone of avoidance. Despite its beauty, the Milky Way has a low surface brightness, which means it can easily be hidden by background light such as moonlight or city lights. For the Milky Way to be clearly seen, the sky must be darker than 20.2 magnitude per square arc second, a level rarely reached in modern cities. If the night sky is dark enough for stars of magnitude plus 5.1 or brighter to be seen, the Milky Way becomes visible, and under even darker skies, with stars visible down to plus 6.1, its fine details stand out clearly. Unfortunately, due to light pollution, more than 1/3 of the world's people can no longer see the Milky Way from where they live. From Earth, the Milky Way's glowing plane passes through 30 constellations. Its centre lies in the direction of Sagittarius, where it shines most brightly. From there, the band stretches around the sky toward Auriga, opposite the galactic centre, and then loops all the way back to Sagittarius, dividing the heavens into two nearly equal parts. The galactic plane is tilted by about 60 degrees compared to the ecliptic, the path the Sun takes through the sky, and by about 63 degrees compared to the celestial equator. This angle gives the Milky Way its sweeping, graceful arch across the heavens, a stunning sight that connects every observer on Earth to the huge structure of the galaxy we call home. Long before telescopes showed the true shape of our galaxy, ancient thinkers tried to explain the mysterious pale band that stretches across the night sky. In his famous work Meteorologica, written in the 4th century before Christ, the Greek philosopher Aristotle described earlier ideas proposed by his predecessors Anaxagoras and Democritus. These early philosophers, who lived between the 5th and 4th centuries before Christ, believed that the Milky Way was a faint glow made by distant stars hidden behind the shadow of the Earth. They thought that while some stars received their light from the sun, others shone too dimly to be seen clearly because their light was drowned out by the brightness of the sun's rays. Aristotle, however, had a different view. He imagined that the Milky Way was not far away in space but part of the upper layer of Earth's atmosphere. He believed it was formed from fiery vapours and sparks left behind by the stars burning in the heavens, which created a glowing circle around the sky. In his explanation, the pale, milky look of the band was the result of light being bent and scattered by the atmosphere itself. Many centuries later, in the 6th century after Christ, the Neoplatonist philosopher Olympiodorus the Younger disagreed with Aristotle's explanation. He pointed out that if the Milky Way truly existed within Earth's atmosphere, its appearance should change depending on one's location or the time of night. Since it always looked the same from anywhere on Earth and did not shift as nearby objects do, he argued that it must instead be part of the celestial world far beyond the moon. This idea of the Milky Way being a structure of the heavens, rather than an atmospheric event, became highly important in later centuries, especially among scholars in the Muslim world. In the 10th and 11th centuries after Christ, the Persian astronomer al-Biruni described the Milky Way as a huge collection of countless bits of cloudy stars. Not long after, in the early 12th century, the Andalusian astronomer Avempais suggested that the Milky Way was actually made up of many tiny stars so close together that they looked like a single bright band in the sky. He even used his observation of a meeting between Jupiter and Mars around the years 1106 or 1107 as proof to support this idea. Another great Persian astronomer, Nasir al-Din al-Tusi, who lived during the 13th century, described the Milky Way in his book Tadhkira as a huge group of very small stars packed tightly together. Because these stars were so many and so close to one another, they looked like pale clouds, which explained why their light looked like milk in colour. Later, the scholar Ibn Qayyim al-Jawziyah, writing in the 14th century, shared a similar belief. He described the Milky Way as a countless number of tiny stars gathered together within the sphere of the fixed stars. The first clear proof that the Milky Way was truly made up of stars came much later, in the year 1610. Using one of the earliest telescopes, Galileo Galilei looked closely at the Milky Way and discovered that it was made of an extremely large number of faint stars packed so closely that their light mixed together. He decided that its hazy look was not from Earth's atmosphere, as Aristotle had thought, but from the combined glow of countless distant suns. More than a century later, in 1755, the philosopher Immanuel Kant built upon earlier ideas suggested by the astronomer Thomas Wright. Kant said that the Milky Way was a huge spinning disk made of billions of stars held together by gravity, just like the planets of the solar system go around the sun, but on a much larger scale. He also said that the faint cloudy nebulae seen in the sky might actually be other island universes, or galaxies, far beyond our own. This term, island universes, would stay popular well into the early 20th century. In 1785, the astronomer William Herschel made the first serious try to map the shape of the Milky Way. By carefully counting the number of stars in different parts of the sky, he created a drawing that showed the Milky Way as a flattened disk with the solar system located near its centre. 60 years later, in 1845, Lord Rosse built a very strong new telescope that let him see details in faraway nebulae. He was the first to tell the difference between those that were elliptical and those that were spiral-shaped. In some of these nebulae, he could even see single stars, giving strong support to Kant's earlier idea that such nebulae might actually be other galaxies. By the start of the 20th century, astronomers were beginning to understand that the Milky Way was not a random group of stars. In 1904, the Dutch astronomer Jacobus Kapteyn studied the movement of stars and noticed that they could be placed into two large streams moving in opposite directions. His findings gave the first hints that the Milky Way was spinning as a whole, a discovery later confirmed by astronomers Bertil Lindblad and Jan Oort. In 1917, the American astronomer Heber Doost Curtis studied a bright nova that showed up in the Great Andromeda Nebula, now known as the Andromeda Galaxy. By comparing it with other novae recorded in pictures, he realized that these objects were much fainter than those found within the Milky Way. From this, he guessed that Andromeda was about 150,000 parsecs away, far beyond the edges of our galaxy. Curtis became a strong supporter of the island universe idea, saying that spiral nebulae were actually separate galaxies. In 1920, the famous Great Debate took place between Harlow Shapley and Heber Curtis. They argued about the true size of the Milky Way and whether spiral nebulae like Andromeda were part of it or different galaxies. Curtis supported the idea of separate galaxies, pointing out that Andromeda had dark dust lanes similar to those seen in the Milky Way, and that its light showed a clear Doppler shift showing great distance. The debate was finally settled in the early 1920s by Edwin Hubble. Using the strong 2.5-meter, 100-inch Hooker telescope at the Mount Wilson Observatory, Hubble was able to take pictures of spiral nebulae in never-seen-before detail. He separated their outer parts into single stars and identified Cepheid variable stars, whose brightness allowed him to measure their distances correctly. Hubble found that the Andromeda Nebula was about 275,000 parsecs from the Sun, far too distant to belong to the Milky Way. This discovery proved without doubt that the universe was far larger than anyone had ever thought, and that the Milky Way was just one of countless galaxies spread across the huge space. The European Space Agency's spacecraft Gaia is one of the most amazing missions in modern astronomy. Its main goal is to measure the distances to stars by carefully watching their tiny shifts in position, known as parallax. With this method, Gaia has been able to estimate the positions and distances of over 1 billion stars, creating the most detailed and exact map of our Milky Way galaxy ever made. Scientists often call the data from Gaia life-changing, because it has completely changed how we understand the structure, movement and growth of our galaxy. Before Gaia, astronomers had trustworthy data for only about 2 million stars back in the 1990s. Thanks to this mission, that number has now grown to an amazing 2 billion stars. The amount of space that can now be measured has grown by 100 times in radius, and the exactness of these measurements has improved by about 1,000 times, letting scientists see our cosmic neighbourhood with never-before-seen clearness. In the year 2020, a major study revealed something surprising. Gaia had found a tiny wobbling movement of the Milky Way itself. Astronomers believe this movement might be caused by several possible things. Maybe the galaxy's disk is slightly tilted compared to its outer halo, or maybe it is being affected by material that fell into it long ago, or even by the gravitational pull of nearby smaller galaxies. In April of 2024, scientists showed the first maps showing the Milky Way's magnetic fields, also made with the help of Gaia's exact observations. Our Sun sits near the inner edge of a spiral arm called the Orion Arm, within a region of interstellar gas and dust known as the local fluff, which itself lies inside a larger space of hot gas called the local bubble. This area lies between two large structures known as the Radcliffe Wave and the Split Linear Structure, which were once thought to be part of a ring called the Gould Belt. Astronomical studies have also helped find how far the Sun is from the very centre of the Milky Way, where a giant black hole known as Sagittarius A sits. Based on calculations by the astronomer Reinhard Genzel and his team in the year 2016, the Sun is about 27,140 light-years from the galactic centre. Another study from the same year, led by Andrea Ghe's team, found a slightly smaller distance of about 25,640 light-years. The Sun is also placed roughly between 16 and 98 light-years above the central plane of the galaxy's disk. The gap between our spiral arm and the next one outward, called the Perseus Arm, is around 6,500 light-years. In an interesting way, our solar system lies in what scientists call the Milky Way's galactic habitable zone, a region thought to have conditions good for life. In the Sun's neighbourhood, there are about 208 stars brighter than absolute magnitude 8.5 within a distance of 49 light-years. That means there is roughly one bright star for every 2,360 cubic light-years of space. However, when all stars are counted, including the faint ones, there are 64 known stars within 16 light-years of the Sun, not counting 4 brown dwarfs. This shows a much higher density, about one star for every 284 cubic light-years. This difference shows that faint stars greatly outnumber bright ones. Across the whole sky, there are only about 500 stars visible to the naked eye brighter than magnitude 4, but more than 15.5 million that are brighter than magnitude 14 and visible through telescopes. The Sun itself is not still. It moves through space, travelling in a general direction known as the solar apex, which points toward the bright star Deneb in the constellation of Cygnus, almost at a right angle to the direction of the galactic centre. The Sun's path around the Milky Way is roughly elliptical, but its orbit is gently changed by the... For many years, some scientists thought these movements might be linked to mass extinction events on Earth, but more recent research has shown no clear link. It takes our solar system about 240 million years to complete one full orbit around the Milky Way. This time is sometimes called a galactic year. Since the Sun was born about 4.5 billion years ago, it has completed between 18 and 20 such orbits around the galaxy, and only a tiny part, about 1/1250th, of a single orbit has passed since humans first appeared on Earth. The solar system moves around the galaxy's centre at about 220 kilometers per second, or roughly 490,000 miles per hour, which is just a tiny part, about 0.07% of the speed of light. Through the surrounding interstellar material of the heliosphere, the Sun travels at about 84,000 kilometers per hour. At this speed, it would take about 1,400 years for the solar system to move a distance equal to 1 light year, or about 8 days to travel 1 astronomical unit, the average distance between the Earth and the Sun. At present, our solar system is moving in the direction of the zodiacal constellation Scorpius, following the plane of the ecliptic, continuing its endless and smooth journey through the huge and shining spiral of the Milky Way. The Milky Way galaxy is divided into 4 main sections called galactic quadrants. These quadrants are like 4 slices of a large circular disk, and they help astronomers describe where stars, nebulae, and other space objects are found within our galaxy. To organise this huge system, scientists use something known as the Galactic Coordinate System, a kind of sky map that places the Sun at the very centre of reference. From this point, the sky is split into 4 numbered areas, the first, second, third, and fourth galactic quadrants, each covering a quarter of the Milky Way's circular shape. When seen from above the northern side of the Milky Way, from a direction high above the galactic centre, the angle known as galactic longitude increases in a counterclockwise direction, starting from 0 degrees at the line running from the Sun through the centre of the galaxy. If, however, someone could look at the galaxy from far below its southern side, that same angle would seem to increase in the opposite clockwise direction. From these different views, the rotation and structure of our galaxy can be better understood. The Milky Way itself is one of the 2 biggest galaxies in our nearby space neighbourhood, called the Local Group, which also includes the large Andromeda Galaxy. However, astronomers still do not fully understand how far the Milky Way's visible disk reaches or how clearly its edges can be marked. Most of the galaxy's stars are found within a width of about 26 kiloparsecs, which equals roughly 80,000 light-years. Beyond this area, the number of stars drops sharply, falling to only a few scattered ones in the far outer parts of the galactic disk. Measuring the size of a galaxy is not easy. Astronomers use several different methods, and each one can give a slightly different answer. The most widely used standard is called D25, which marks the edge of a galaxy based on how its brightness slowly fades toward the outer parts. More exactly, this point is where the galaxy's brightness in blue light, around a wavelength of 445 nanometers, becomes faint enough to reach a value of 25 magnitudes per square arc second. In 1997, astronomer Peter Goodwin and his team compared the brightness of certain stars known as Cepheid variables in 17 other spiral galaxies to those in the Milky Way. By studying these data, they estimated our galaxy's visible width to be about 26.8 kiloparsecs, or roughly 87,400 light-years. They based this on a model in which the Milky Way's disk follows an exponential shape, with a central brightness of about 22.1 blue magnitudes per square arc second and a disk scale length of around 5 kiloparsecs, equal to 16,300 light-years. This result suggests that the Milky Way is a little smaller than the Andromeda Galaxy, and slightly below the average size of other spiral galaxies, which are around 28 kiloparsecs wide, or about 92,000 light-years. This means that, unlike earlier beliefs, our galaxy and Andromeda are not extremely large among spirals, but rather quite normal in size. To make this easier to picture, if the solar system, reaching out to Neptune, were the size of a US quarter coin, a bit less than 1 inch across, the Milky Way would stretch roughly across the entire width of the continental United States. An older study from 1978 gave a smaller guess for the galaxy's width, about 23 kiloparsecs or 75,000 light-years. In 2015, astronomers found a large ring-shaped group of stars called the Triangulum Andromeda Ring, also known as the Triand Ring, which seems to wave up and down above and below the otherwise flat plane of the Milky Way. Together with another structure called the Monoceros Ring, this ring may be part of the galaxy's stretched outer disk, possibly reaching a width of at least 50 kiloparsecs, or about 160,000 light-years. However, a later study in 2018 suggested a different idea, that these rings may actually be stars that were once part of the main disk, but were pushed outward by gravity, forming what astronomers call stellar overdensities. Another study, also released in 2018, found signs that the Milky Way's disk may reach even farther than earlier thought, maybe as far as 31.5 kiloparsecs, or about 103,000 light-years from the galactic centre. This was surprising, since earlier research hinted that the galaxy's star-filled area ended at around 20 kiloparsecs, or 70,000 light-years. Even more surprising results came in 2020, when astronomers estimated the edge of the Milky Way's dark matter halo, the unseen sphere of strange material surrounding the galaxy, to be about 292 kiloparsecs, or roughly 952,000 light-years from the centre. This means the entire dark matter halo could stretch nearly 1,900,000 light-years across. The Milky Way's main star-filled disk, where most of its stars, nebulae and planetary systems lie, is estimated to be about 1 1/3 kiloparsecs thick, which equals roughly 4,000 light-years. The Milky Way galaxy is a huge system whose total mass is estimated to be about 880 billion times the mass of the Sun, when measured up to a distance of about 200,000 light-years from its centre. However, astronomers do not all agree on the exact amount, because different methods and observations give slightly different answers. Some studies suggest that the Milky Way might weigh as little as 580 billion solar masses, which would make it a bit smaller than our neighbouring Andromeda galaxy. In the year 2009, measurements using a network of radio telescopes called the Very Long Baseline Array showed that some stars near the outer edge of our galaxy move at speeds as high as 254 kilometers per second, which is about 570,000 miles per hour. Because a star's orbital speed depends on the total mass inside its orbit, these results suggested that the Milky Way might be much heavier than earlier thought, possibly as massive as Andromeda, with around 700 billion solar masses within about 160,000 light-years of its centre. The following year, in 2010, another measurement based on the movement of stars in the galactic halo found a similar amount, estimating 700 billion solar masses within about 80,000 light-years. A few years later, in 2014, new studies placed the total mass of the Milky Way at around 850 billion solar masses, which is roughly half that of the Andromeda galaxy. Then, in 2019, astronomers suggested an even higher number, about 1,290 billion solar masses. A large part of the Milky Way's mass is not made of visible stars or gas, but of dark matter, a strange and unseen kind of matter that gives off no light but still has gravity. Scientists believe that this dark matter forms a huge, nearly round halo that reaches more than 100,000 light-years beyond the galactic centre. Models of the Milky Way suggest that this dark matter alone could have a mass of between 1 trillion and 1.5 trillion solar masses. Some studies from 2013 and 2014 offered a wider range from as small as 800 billion to as large as 4.5 trillion solar masses. In comparison, the total mass of all the stars in the Milky Way is thought to be between 46 billion and 64 billion solar masses. Apart from stars, the galaxy also contains large amounts of interstellar gas, made up of about 90% hydrogen and 10% helium by weight. About 2/3 of the hydrogen is in atomic form, while the remaining third is in molecular form. The total mass of this gas is roughly 10 to 15% of the mass of all the stars in the galaxy. There is also a small amount of interstellar dust, which makes up about 1% of the gas's total mass. In March of 2019, astronomers reported that the virial mass of the Milky Way, a measure that includes all the matter held together by gravity, was about 1,540 billion solar masses within a distance of roughly 130,000 light-years. This was more than twice the value found in earlier studies, and suggested that nearly 90% of the Milky Way's total mass might be dark matter. However, in September of 2023, new data from the Gaia spacecraft gave a much lower estimate, suggesting a virial mass of only 206 billion solar masses, about 1/10 of earlier measurements. The Milky Way is home to between 100 billion and 400 billion stars, and it likely has at least that many planets. The exact number is unclear because the smallest and faintest stars are extremely hard to detect, especially those found more than 300 light-years from the Sun. In comparison, the nearby Andromeda Galaxy may contain about 1 trillion stars. Within our galaxy, astronomers estimate there are about 10 billion white dwarfs, 1 billion neutron stars, and around 100 million black holes. Between the stars lies a wide, thin layer of gas and dust known as the interstellar medium. This disk stretches as far outward as the stars themselves, and its thickness changes, from a few hundred light-years in the cooler areas to several thousand light-years in the warmer ones. The Milky Way's disk does not have a sharp outer edge. Instead, the number of stars slowly becomes smaller as one moves away from the galactic center. Beyond about 40,000 light-years from the center, the number of stars drops much faster. Surrounding the main disk is a huge halo of old stars and ancient globular clusters, reaching outward until it is limited by the paths of the galaxy's two main satellite companions, the Large and Small Magellanic Clouds. These small galaxies come as close as 180,000 light-years from the Milky Way's center. If objects in the halo orbited beyond this distance, their paths would likely be disturbed by the gravity of the Magellanic Clouds, possibly pushing them out of the Milky Way's area. The Milky Way's total brightness in visible light is estimated to have an absolute brightness of about -20.9, making it one of the brighter galaxies in our local group. Astronomical studies have shown that there may be at least one planet for every star in the Milky Way. Some studies even say that there are more free-floating planets, ones not tied to any star, than there are stars themselves. According to a 2013 study of the five-planet system Kepler-32, the Milky Way likely has between 100 billion and 400 billion planets. Another study from that same year guessed that at least 17 billion of those planets are roughly Earth-sized. Later, in November of 2013, information from the Kepler Space Telescope showed that there could be as many as 40 billion Earth-sized planets moving within the livable zones of stars like the Sun and of smaller red dwarfs. About 11 billion of these could be moving around stars like our Sun. The closest known Earth-sized exoplanet is thought to be Proxima Centauri b, which is about 4 2/10 light-years away, according to a 2016 study. Smaller, rocky planets like Earth seem to be much more common than large gas giants, though they are harder to find because of their size and dimness. Scientists have even found signs of exocomets, icy objects moving around other stars, which may also be common in our galaxy. In November of 2020, researchers guessed that there could be over 300 million possibly livable planets in the Milky Way alone. Interestingly, when compared to more distant galaxies, the Milky Way produces a fairly low number of neutrinos, ghost-like particles that almost never interact with matter, leading astronomers to call our galaxy a neutrino desert. The Milky Way galaxy is made of a bright bar-shaped center, surrounded by a huge bent disk of stars, gas, and dust. Its shape closely matches what astronomers group as a type SBC spiral galaxy, one with loosely wound arms that curl gently outward from the center. Scientists began thinking during the 1960s that the Milky Way might not be a simple spiral galaxy, but instead a barred spiral one, meaning that its middle area is stretched into a long bar shape. This idea was later proven in the year 2005, when the Spitzer Space Telescope showed that the Milky Way's center bar was even bigger than astronomers had thought. Our Sun is located about 25,000 to 28,000 light-years from the very middle of the Milky Way. Astronomers guess this distance using different geometric methods, and by studying special kinds of stars known as standard candles that help measure cosmic distances with better accuracy. The inner area of the galaxy, about 10,000 light-years from the center, holds a thick bunch of mostly ancient stars known as the galactic bulge. Some scientists think that the Milky Way may not have a true bulge at all, but instead a fake bulge made by the movement of stars within its center bar. Others say that what looks like a bulge might just be a peanut-shaped structure caused by gravitational instabilities within that bar. At the very centre of our galaxy lies a strong and mysterious radio source called Sagittarius A star. The movement of gas and stars swirling around it shows the presence of a huge unseen object, a supermassive black hole guessed to weigh between 4 million and 4.5 million times as much as our Sun. This black hole is fairly quiet, pulling in matter at a very slow rate, only about 100,000th of a solar mass each year, which means it is currently inactive compared to the centres of some other galaxies. Studies suggest that nearly all big galaxies hold such giant black holes at their centres. The exact size and shape of the Milky Way's centre bar are still being discussed. Estimates place its half-length between about 3,000 and 16,000 light-years, tilted by roughly 10 to 50 degrees from our view toward the galactic centre. Some astronomers even think that our galaxy might have two bars, a smaller one inside a bigger one, although this idea is still debated. The bar is thought to be surrounded by a structure known as the 5 kiloparsec ring, which holds much of the Milky Way's molecular hydrogen and is one of the most active areas for star-making. If we could see our galaxy from the nearby Andromeda Galaxy, this bright ring would stand out as one of the brightest features of the Milky Way. In June of the year 2023, a research team led by Naoko Kurahashi-Nielsen used a new cascade neutrino detection method to observe, for the first time, neutrinos coming straight from the galactic plane of the Milky Way, giving humanity its first ever neutrino picture of our home galaxy. Since the year 1970, several space missions have picked up gamma rays with an energy of 511 kilo-electron volts coming from the direction of the galactic centre. These rays are made when positrons, which are particles of antimatter, hit and cancel out with electrons. In 2008, scientists found that the sources of these gamma rays follow a pattern similar to that of low-mass X-ray binary systems, pairs of stars where one is a small, dense object like a neutron star. This finding suggested that such systems might be releasing positrons into space, where they meet electrons and vanish in bursts of radiation. The giving-off region was found to stretch about 10,000 light-years and shine with a brightness roughly equal to 10,000 suns. Then, in 2010, astronomers found two huge balloon-like structures rising above and below the Milky Way centre. Each of these Fermi bubbles, as they were called, reaches about 25,000 light-years across, roughly 1/4 of the galaxy's full width. They reach all the way into the regions of the sky, where the constellations Grus and Virgo are located. Later studies using the Parkes radio telescope showed that these bubbles are linked to strong magnetized outflows, likely caused by bursts of star-making in the galaxy's centre, 200 parsecs, or about 640 light-years. On the 5th of January 2015, NASA picked up an unusual X-ray flare from Sagittarius A star, about 400 times brighter than its normal output. This record-breaking burst might have been caused by a small asteroid being ripped apart as it fell into the black hole, or possibly by magnetic field lines snapping and connecting again within the swirling gas around it. Beyond the reach of the galactic bar, the Milky Way's disk holds 4 large spiral arms made of stars, gas, and dust. These arms are areas where interstellar material is thicker than average, and where many new stars are born within glowing hydrogen clouds and giant molecular structures. However, astronomers still do not fully agree on the exact layout of these arms. The Milky Way's spiral pattern is not a perfect geometric spiral. Its arms often split, join, and twist in complex, uneven ways. The Sun itself seems to be located inside a smaller offshoot of one of these arms, known as the local arm, which shows that the galaxy's structure is far from even. The angle at which the arms curve outward from the centre, known as the pitch angle, is thought to be between about 7 and 25 degrees. The Milky Way's spiral structure is far more detailed and interesting than it may look from Earth. Within the Sun's orbit around the galaxy's centre lie 2 of its spiral arms, the Scutum Centaurus arm and the Carina Sagittarius arm. These arms are special because they touch what astronomers call tangent points, places where the line of sight from the Sun runs straight along the length of an arm. If these spiral arms truly have more stars than the average parts of the galactic disk, this difference should be seen by counting the number of stars in those places. When astronomers studied these areas using near-infrared light, a type of light that can pass through the thick clouds of cosmic dust, they found something surprising. The Scutum Centaurus arm held about 30% more red giant stars than expected, proving that it is indeed a major star-filled arm. However, the same increase was not seen in the Carina Sagittarius arm, suggesting that the Milky Way may have only two big arms filled with old stars, the Perseus arm and the Scutum Centaurus arm. The other arms seem to have mostly gas and fewer old stars. Later, in December of the year 2013, astronomers studying young stars and star-making areas found that these followed a pattern of 4 spiral arms. This means that, while the Milky Way has 2 major arms rich in old stars, it seems to have 4 arms made up of gas and young stars. The reason for this strange difference between the two findings is still unknown. In the 1950s, astronomers led by Hendrik van Woerden made another important discovery. Using radio waves with a wavelength of 21 centimeters to study atomic hydrogen, they found a structure now called the near 3 kiloparsec arm, sometimes simply the 3 kiloparsec arm. This arm was found to be moving away from the Milky Way's central bulge at a speed greater than 50 kilometers per second. It lies in the 4th galactic quadrant, about 5 2/10 kiloparsecs from the Sun, and around 3 3/10 kiloparsecs from the galactic center. Many years later, in the year 2008, astronomer Tom Dame discovered another similar feature, the far 3 kiloparsec arm in the 1st galactic quadrant, located about 3 kiloparsecs, or roughly 10,000 light-years, from the galactic center. A computer simulation published in the year 2011 suggested that the Milky Way's spiral shape might have been formed through repeated crashes with a much smaller galaxy, the Sagittarius Dwarf Elliptical Galaxy. Some researchers also believe that our galaxy might have 2 different spiral patterns, an inner one, formed by the Sagittarius arm, which turns quickly, and an outer one formed by the Carina and Perseus arms, which turn more slowly and are more tightly wound. This slower outer pattern could create a structure that looks like a ring, sometimes called a pseudo-ring, with the Cygnus arm acting as a bridge between the two systems. Beyond these main spiral arms lies a mysterious feature known as the Monoceros ring, or outer ring, a huge loop of gas and stars that may have been pulled from smaller galaxies billions of years ago. However, some scientists now believe that this ring is not a separate structure at all, but instead a region of the Milky Way's disk where stars are more tightly packed because of its bent and stretched shape. In fact, the Milky Way's disk itself is not perfectly flat. It bends and twists into a gentle S shape as it spreads outward. Surrounding this great disk is a roughly round halo filled with ancient stars and tight clusters, known as globular clusters. About 90% of these clusters are found within 100,000 light-years of the galactic center, though a few, like PAL4 and AM1, are located more than 200,000 light-years away. Interestingly, around 40% of these clusters move in the opposite direction to the Milky Way's overall spin, following looping or rosette-shaped paths rather than smooth oval orbits like planets around stars. While the disk is filled with clouds of dust that block certain types of light, the halo is much clearer. New stars are constantly being born within the disk, especially inside the spiral arms where gas and dust are thick, but almost no star formation happens in the halo, where there is very little cool gas left. Groups of young stars known as open clusters are also found mainly within the disk. In the early years of the 21st century, astronomers made new discoveries that expanded our understanding of the Milky Way structure. Observations showed that the disk of the nearby Andromeda Galaxy stretches much farther than earlier believed, suggesting that our own galaxy's disk might do the same. Evidence for this comes from the detection of the outer arm extension of the Cygnus arm and another similar extension of the Scutum Centaurus arm. When astronomers discovered the Sagittarius Dwarf Elliptical Galaxy, they also noticed a long line of stars, leftovers being pulled apart by the Milky Way's gravity as this smaller galaxy orbits around it. In the year 2004, scientists found another ring-like structure made of star debris moving in the same plane as the Milky Way. At first, this was thought to be the remains of a small system called the Canis Major Dwarf Galaxy, but later studies suggested that it was actually part of the Milky Way's natural bend, an idea supported by more evidence as of the year 2021. The Sloan Digital Sky Survey of the Northern Sky revealed a huge, faint structure within our galaxy, covering an area about 5,000 times bigger than the full moon. This group of stars rises almost straight up from the plane of the Milky Way's spiral arms, and astronomers believe it could be the remains of another small galaxy joining with ours. This mysterious feature has been tentatively named the Virgo Stellar Stream and lies in the direction of the constellation Virgo, about 30,000 light-years away. High above and beyond the stars of the Milky Way, there exists not only a halo made up of ancient stars, but also a vast and mysterious ocean of gas. Observations from the Chandra X-ray Observatory, XMM Newton, and the Japanese satellite Suzaku have revealed this hidden, glowing halo of hot gas that stretches hundreds of thousands of light-years into space, far beyond the Milky Way's star-filled edge and nearly as far as the Large and Small Magellanic Clouds. This gas halo is not just an empty fog, it is huge in mass, holding almost as much matter as the entire Milky Way itself. The temperature of this hot gas burns between 1 and 2.5 million kelvins, which is roughly between 1.8 and 4.5 million degrees Fahrenheit. In the earliest ages of the universe, when it was only a few billion years old, astronomers have found that there was about 1 part of ordinary, or baryonic, matter for every 6 parts of dark matter. Yet today, when they look around nearby galaxies like our own, only about half of that ordinary matter can be seen. If it is true that this enormous halo of hot gas really weighs as much as the Milky Way, it might finally reveal where those long-lost baryons have been hiding, floating unseen around our galaxy all this time. Inside the Milky Way, both stars and gas swirl around the galactic center in a graceful, complex dance. Unlike the planets of the solar system, which move faster the closer they are to the Sun, the stars in the Milky Way move at almost the same speed no matter how far they are from the center. Most of them race along at about 200 to 220 kilometers per second, completing huge orbits over millions of years. This smooth, almost constant motion is a mystery because if the galaxy contained only the visible matter we can see, its stars, gas and dust, the speed of rotation should slow down farther from the center. But it doesn't. The flatness of the Milky Way's rotation curve shows that there must be something else, something invisible, adding to its gravity. This unseen matter, known as dark matter, appears to make up most of the galaxy's total mass. A few scientists, however, think that maybe gravity itself behaves differently on such huge scales, but most astronomers agree that dark matter is the best explanation. The Milky Way's story began more than 13.5 billion years ago, shortly after the great event known as the Big Bang. Tiny ripples and clumps in the young universe's matter began to grow under the pull of gravity, and some of these dense areas became the seeds of what would one day form globular clusters round swarms of ancient stars that still float in the Milky Way's halo today. Over time, nearly half of the matter that now makes up the Milky Way may have drifted in from other galaxies. Within only a few billion years, the growing galaxy spun faster and faster, and as it did, the swirling clouds of gas flattened into a great turning disk. From this disk, new generations of stars were born, among them our own Sun. As ages passed, the Milky Way continued to grow. It joined with other small galaxies, pulling them into its spiral body, and even now it continues to draw in its smaller neighbours. Two of its biggest companions, the Large and Small Magellanic Clouds, are slowly being pulled in through long streams of gas known as the Magellanic Stream. Even high-speed clouds such as the Smith Cloud are falling toward the Milky Way, adding new material to its halo. Simulations of cosmic history suggest that about 11 billion years ago, the Milky Way went through a major joining with a large galaxy astronomers have nicknamed the Kraken. Since then, surprisingly, it seems that our galaxy has avoided any crashes with other large galaxies for almost 10 billion years, a rare quiet time in galactic history. In contrast, our neighbouring Andromeda galaxy has had a far more eventful past, shaped by many more joinings with large galaxies. Today, both the Milky Way and Andromeda sit in a special place in what astronomers call the Galaxy Colour Magnitude Diagram. They are in the Green Valley, an area between the bright blue cloud of galaxies still making stars and the red sequence of older galaxies where starbirth has nearly stopped. This means that the Milky Way's ability to make new stars is slowly fading as it runs low on the raw gas needed for star formation. Computer simulations show that within about 5 billion years, the Milky Way will probably stop forming stars altogether, though before that happens, its crash with the Andromeda galaxy may briefly spark a burst of new star-making. Even now, the Milky Way is among the brightest and reddest of all spiral galaxies that still make new stars. Yet compared to the oldest and reddest galaxies, it still shines with a faint touch of young blue light, a sign that life and activity still exist within its great spiral arms. To understand just how old the Milky Way really is, astronomers study its oldest remaining members, globular clusters. These ancient star groups give us a minimum age for the galaxy. Scientists also measure the amounts of long-lasting radioactive elements like thorium-232 and uranium-238 in old stars. By comparing how much is left to how much there once was, they can estimate the star's ages using a method called nucleocosmochronology. This method shows that some stars, like the star named CS 31082-001, are about 12.5 billion years old, while others, like BD plus 17 degrees 3248, may be as old as 13.8 billion years. White dwarfs, stars that have burned out and are slowly cooling, also act as cosmic clocks. By measuring how cool the oldest white dwarfs have become, astronomers estimate that the globular cluster known as M4 is about 12.7 billion years old. The oldest clusters in the Milky Way seem to be around 12.5 billion years old, with an upper possible limit of about 16 billion years. In November 2018, astronomers made an amazing discovery. One of the oldest known stars in the universe, the tiny ancient star called 2MASSJ, 1808202 -51043778b, nearly 13.5 billion years old, is made almost entirely of original material from the Big Bang itself. Its presence in our Milky Way suggests that our galaxy may be at least 3 billion years older than once thought, going back almost to the beginning of time. Several individual stars have been found in the far outer regions of the Milky Way, called its halo, whose ages are very close to the estimated age of the universe, about 13 billion and 800 million years. One notable example, discovered in 2007, is a star named He1 523-0901. Astronomers estimated its age to be about 13 billion and 200 million years, making it at that time the oldest known object in our galaxy. This ancient star helped scientists set a minimum age for the Milky Way itself. To figure out its age, astronomers used a very sensitive tool called the UV Visual Echelle spectrograph on the Very Large Telescope in Chile. This tool studied the star's light and measured the strength of certain spectral lines. Faint signals made by elements like thorium and others formed in powerful nuclear reactions known as the R process. By comparing the amounts of these elements and their types, researchers could calculate how long ago they were made, using a method called nucleocosmochronology, which is basically a kind of cosmic radioactive dating. Another interesting star, named HD 140283, has also drawn attention. Its age has been estimated several times, with results ranging between about 12 billion and 13 billion 700 million years, depending on the study and method used. Stars in the dense central bulge of the Milky Way, according to detailed observations corrected for Earth's atmospheric effects using adaptive optics, have been found to be about 12 billion and 800 million years old. The stars in the galaxy's thin disk, the flat area where most stars, gas and dust are usually younger. Using the same nucleocosmochronology method, astronomers estimate that this disk began forming about 8 billion and 800 million years ago, with a possible uncertainty of about 1 to 2 billion years. This suggests that there was a long pause, nearly 5 billion years, between the formation of the Milky Way's halo and the creation of its thin disk. Further chemical studies of thousands of stars show that star formation dropped sharply between 10 and 8 billion years ago, likely because the gas in space had become too hot and rough to form new stars easily. Around the Milky Way are many smaller companion galaxies, but they are not scattered randomly. Instead, they seem to form a large ring-like structure about 500,000 light-years across and 50,000 light-years thick. Astronomers think this pattern may have formed long ago when a bigger system broke apart. Close encounters between galaxies, like the one expected about 4 billion years from now between the Milky Way and the Andromeda Galaxy, can pull away huge streams of gas. Over time, these streams can condense into new small galaxies that orbit in rings at different angles to the main galactic disk. The Milky Way and Andromeda Galaxy together make a kind of cosmic pair, a binary system of two giant spiral galaxies. They belong to a group of about 50 galaxies called the local group. This local group is surrounded by a large empty space called the local void, and sits within a bigger structure called the local sheet, which is part of the huge Virgo supercluster. Around this supercluster are several massive empty regions: the microscopium void to the north, the sculptor void to the left, the Boötes void to the right, and the Cain's major void to the south. These voids are not still. They slowly shift and change shape over time, forming long web-like structures of galaxies called filaments. The Virgo supercluster is itself being pulled toward an even larger gravitational area, called the Great Attractor, which is part of a giant cosmic structure called Laniakea, the main home of our galaxy and the universe. Among the Milky Way's companions, the largest are the Large and Small Magellanic Clouds, two irregular small galaxies. The Large Magellanic Cloud is about 32,200 light-years wide and orbits close to its smaller partner. Stretching out from them is the Magellanic Stream, a long ribbon of neutral hydrogen gas that spans 100 degrees of the night sky. This stream was likely pulled from the two galaxies by the Milky Way's gravity during past encounters. Several other smaller dwarf galaxies circle the Milky Way as well, including the Canis Major Dwarf, the closest one, along with the Sagittarius Dwarf elliptical galaxy, the Ursa Minor Dwarf, the Sculptor Dwarf, the Sextans Dwarf, the Fornax Dwarf, and the Leo 1 Dwarf. The smallest of these, like the Carina Dwarf, Draco Dwarf, and Leo 2 Dwarf, are only about 500 light-years wide, tiny compared to the Milky Way itself. Astronomers keep finding more of these faint companions. In 2015, 9 new satellite galaxies were found in just a small patch of the sky. Some dwarfs have already merged into the Milky Way, including the ancient parent of the big globular cluster called Omega Centauri. In 2005, and confirmed again in 2012, scientists reported an amazing discovery. Most of the Milky Way's satellite galaxies are arranged in a single huge disk and move in the same general direction. This surprised cosmologists because usual galaxy formation theories predict that such satellites should form in dark matter halos and move randomly. The reason for this unusual pattern remains a deep cosmic mystery. Another interesting discovery came in January 2006, when researchers finally explained the strange warp of the Milky Way's disk. Using detailed mapping, they found that the distortion is actually a ripple, a vibration caused by the gravity of the Large and Small Magellanic Clouds as they orbit the Milky Way. Although these two galaxies contain only about 2% of the Milky Way's mass, computer simulations showed that their movement through the galaxy's outer edges creates a wake in the dark matter, increasing their effect and causing the galactic disk to wobble like a disturbed pond. Today, precise measurements show that the Andromeda Galaxy is moving toward the Milky Way at about 100 to 140 kilometers per second, or roughly 220,000 to 310,000 miles per hour. In about 4 billion and 300 million years, the two galaxies are expected to collide. Even so, the chance of any two stars hitting each other is very small, because the distances between them are huge. Instead, their gravity will slowly merge the Milky Way and Andromeda into one huge galaxy, probably an elliptical or maybe a massive disc-shaped one, over about 6 billion years, changing the night sky forever. According to Einstein's special relativity theory, there is no single preferred or absolute frame of reference in space from which we can measure the Milky Way's motion. However, when astronomers study the galaxy in relation to the large-scale structure of the universe, they can describe its movement compared to certain cosmic reference frames. One such reference frame is called the Hubble flow, the obvious movement of galaxies and galaxy clusters caused by the overall stretching of the universe itself. Every galaxy, including our Milky Way, has what scientists call a peculiar velocity, meaning its own unique movement that is slightly different from the smooth outward expansion of space. To properly compare the Milky Way's motion with the Hubble flow, astronomers must look at a very large part of the universe, big enough that the cosmic expansion becomes much more important than the smaller, random movements of single galaxies. In such a huge area, the average movement of all galaxies matches the general expansion, or the Hubble flow. Based on careful measurements, astronomers estimate that the Milky Way is moving at about 630 kilometers per second, which is roughly 1,400,000 miles per hour, compared to this large-scale cosmic frame of reference. This huge speed carries our galaxy generally toward a mysterious region called the Great Attractor, a gravitational pull affecting many nearby galaxies, as well as toward the Shapley supercluster, which lies beyond it. Our galaxy, along with the Andromeda Galaxy and many smaller neighbours, forms a small group of galaxies held together by gravity called the Local Group. This group is part of an even larger structure called the Local Supercluster, which is centred near the Virgo cluster. Although the Local Group and the Virgo cluster are moving apart at about 967 kilometers per second, or roughly 2,160,000 miles per hour, this speed is still slower than what would be expected from the general expansion of the universe at their huge distance of about 16.8 million parsecs. This slower movement is thought to be caused by the strong gravitational pull between these huge cosmic structures. Another important way to measure the Milky Way's motion is through the cosmic microwave background, CMB, which is the faint leftover glow from the birth of the universe. In this reference frame, scientists look for the spot where the CMB's temperature seems most even, showing no Doppler shift or change. When studied this way, the Milky Way is found to be moving at about 552 km per second, plus or minus 6 km per second, which is about 1,235,000 miles per hour, toward a point in the sky near the constellation Hydra, at about 10.5 hours of right ascension and 24 degrees south declination. This motion has been directly seen by satellites such as the Cosmic Background Explorer, COBE, and the Wilkinson Microwave Anisotropy Probe, WMAP. These spacecraft detect a small pattern in the CMB called the dipole anisotropy, a difference in temperature caused by the Milky Way's movement. In the direction the galaxy is moving, the CMB light looks slightly blue-shifted, meaning its waves are squeezed and therefore hotter, while in the opposite direction, it looks red-shifted, meaning its waves are stretched and cooler. This cosmic mark gives one of the clearest and most accurate measurements of our galaxy's fast journey through the universe. Messier 82, also called NGC 3034, the Cigar Galaxy, or simply M82, is one of the most interesting and active galaxies in our nearby universe. It is about 12 million light-years away from Earth in the northern constellation of Ursa Major, the Great Bear. In its group of nearby galaxies called the M81 group, it is the second largest member. Across its visible size, measured as a D25 esophotal diameter, it stretches about 12.52 kiloparsecs, or roughly 40,800 light-years. This galaxy shines with amazing brightness. It is almost 5 times brighter than our Milky Way, and its central area alone glows about 100 times more brightly. The reason for this strong light is the galaxy's unusual starburst activity, a cosmic fireworks show where new stars are forming very quickly. Astronomers think this burst of star creation was caused by the pull and interaction with its nearby galaxy, M81. Because of its closeness to Earth and its extreme star-forming activity, M82 is often seen as the perfect example, or model, of a starburst galaxy. In the year 2014, astronomers saw a dramatic event in M82, a bright type Ia supernova named SN 2014J exploded on the 21st day of January. That same year, researchers also found an unusual pulsar, an extremely dense, fast-spinning remnant of a massive star, called M82X2. It turned out to be the brightest pulsar ever found, a record-breaking cosmic lighthouse shining across space. Almost 10 years later, in November of 2023, another amazing event happened. Astronomers saw a strong gamma-ray burst coming from M82. Careful study showed that the explosion was made by a magnetar, a type of neutron star with an incredibly strong magnetic field. This was the first time such an event had been seen outside our Milky Way galaxy, and only the 4th time ever recorded anywhere in the universe. The story of M82 goes back much further. It was first seen in the year 1774 by the German astronomer Johann Elert Bode, who described it as a faint hazy patch of light about 3/4 of a degree away from another similar object, M81. Just a few years later, in 1779, the French astronomer Pierre Méchain independently found both galaxies and reported them to Charles Messier, who soon added them to his famous list of celestial objects. For a long time, M82 was thought to be an irregular galaxy, meaning it had no clear shape or spiral arms. But in 2005, new observations using near-infrared light showed something surprising: 2 smooth spiral arms hidden in the galaxy's bright disk. These arms had gone unnoticed before because the galaxy is seen almost edge-on from Earth, tilted at about 80 degrees, and its central areas are wrapped in thick, dusty filaments that block visible light. When astronomers carefully removed the background glow from their infrared images, the spiral arms became visible. They looked bluer than the disk, meaning they were full of young, hot stars. The arms seem to curve outward from the ends of a central bar of stars, stretching across roughly 3 times the width of the disk. That same year, the Hubble Space Telescope showed an incredible sight in M82's core: 197 massive clusters of newly formed stars. Each of these clusters had on average about 200,000 times the mass of our Sun, making the galaxy's heart a very active and crowded place. New stars there are being born about 10 times faster than in the whole Milky Way galaxy combined. At the very centre of M82 is a powerful starburst area about 500 parsecs across. In this small space, astronomers found 4 especially bright zones labelled A, C, D, and E. These clumps shine strongly in visible light and also match known sources of X-rays, infrared light, and radio waves. The galaxy's famous superwind, a huge outflow of gas and dust caused by exploding stars, seems to come mostly from clumps A and C. Supernovae happen there about once every 10 years, giving enough energy to push matter out of the galaxy's core into space like smoke from a cosmic chimney. The Chandra X-ray Observatory later found strange, flickering X-rays about 600 light-years from the galaxy's centre. Astronomers think they might come from a rare type of black hole, one that is medium-sized with a mass about 205,000 times that of the Sun. Like most big galaxies, M82 also has a supermassive black hole at its centre, weighing about 30 million times the mass of the Sun, as seen from the motion of nearby stars. In April of 2010, radio astronomers at the Jodrell Bank Observatory in the United Kingdom found something unexpected in M82. They saw a new radio source that started sending unusual signals unlike anything seen before. The object's strange behaviour was hard to explain. Some scientists said it might be a rare kind of microquasar, a small but powerful object that shoots jets of material at nearly the speed of light. But unlike known microquasars, this one showed very little X-ray light, so little that it could not be measured. The strange object is a few arc-seconds away from the galaxy's centre, making it unlikely to be directly linked to its supermassive black hole. Even more confusing, it seems to be moving at a speed 4 times faster than light. This illusion of faster-than-light motion happens when strong jets of material move almost directly toward us at very high speeds, creating the appearance of superfast travel. Messier 82, also called the Cigar Galaxy, lives under the strong influence of its bigger neighbour, the grand spiral galaxy Messier 81. The two galaxies are in a cosmic dance, and the pull of Messier 81's gravity has slowly stretched and reshaped Messier 82 for about 100 million years. This gravitational tug has stirred up the gas and dust inside Messier 82, causing a big increase in star formation, about 10 times more than in normal galaxies. Over the past 200 million years, Messier 82 has had at least one major tidal interaction with Messier 81. During this time, huge streams of gas were pulled toward the galaxy's centre. The strongest of these interactions likely happened between 200 million and 500 million years ago, starting a huge burst of star formation in the galaxy's heart. This starburst phase lasted up to 50 million years, with new stars being born at a rate of about 10 times the mass of our Sun every year. After that, 2 more smaller starbursts happened, with the latest one about 4 to 6 million years ago. This last event created the galaxy's bright central clusters, a mix of very big superstar clusters and smaller ones. Further out in the disk of Messier 82, most stars were made during a big wave of star formation about 500 million years ago. This filled the galaxy's disk with hundreds of young clusters that look like the old globular clusters in our Milky Way, though they are much younger. Around 100 million years ago, this outer star formation stopped completely. Since then, almost all new star formation in Messier 82 has been limited to its bright, active centre, with only a little activity continuing in the outer halo over the past 1 billion years. Scientists think that long ago Messier 82 might have been a faint, low-brightness galaxy, quiet and calm. Its violent change likely started when it came under the pull of the massive Messier 81, which awakened the galaxy's hidden potential and triggered its amazing bursts of star formation. When seen from Earth, the centres of Messier 81 and Messier 82 appear to be about 130,000 light-years apart. Their real distance from each other is estimated to be around 300,000 light-years, more or less. Because it is a starburst galaxy, Messier 82 often produces supernovae, huge explosions marking the deaths of massive young stars. The first candidate for a supernova in this galaxy, called SN 1986d, was later found not to be a real supernova but a variable infrared source instead. The first confirmed supernova in Messier 82 was found in March of 2004. Called SN 2004 AM, it was seen in images taken a few months earlier, in November of 2003, by the Lick Observatory Supernova Search. Scientists later identified it as a Type II supernova, the explosive collapse of a massive star. In the year 2008, astronomers noticed a mysterious burst of radio waves coming from a distant galaxy, later named SN 2008-IZ. This strange event was probably another supernova, a massive stellar explosion, but it had been hidden behind thick clouds of gas and dust, making it invisible to ordinary telescopes that detect normal light. A similar radio-only signal appeared the following year, in 2009, although it was never officially confirmed or given a name. Before the era of modern, high-resolution surveys, astronomers suspect that many more supernovae must have occurred in Messier 82 during earlier decades, quietly leaving their marks behind. In the 1980s and 1990s, the European Very Long Baseline Interferometry Network studied several potential supernova remnants within the galaxy. One of these remnants clearly expanded between the years 1986 and 1997, suggesting that the original explosion had likely taken place in the early 1960s. Two other remnants also showed signs of possible expansion, but their exact ages remained uncertain. Then, on the 21st of January 2014, at 19 hours and 20 minutes Universal Time, a bright new point of light suddenly appeared in Messier 82. This discovery was made by astrophysics lecturer Steve Fossey and 4 of his students at the University of London Observatory. Initially, the object had an apparent brightness, or magnitude, of about plus 11.7. Within just 2 days, it had grown brighter, reaching plus 10.9. Examining earlier photographs revealed that this cosmic explosion had begun brightening between the 14th and the 20th of January, climbing from magnitude plus 14.4 to plus 11.3. At first, astronomers were hopeful it might become even brighter, possibly reaching plus 8.5, bright enough to be seen through small telescopes or even large binoculars. However, by the end of January it peaked at a slightly dimmer magnitude of plus 10.5. Careful study soon confirmed that this was a young reddened Type Ia supernova, caused by the violent explosion of a white dwarf star in a binary star system. The International Astronomical Union officially named it SN 2014J. Interestingly, Messier 82's neighbouring larger galaxy, Messier 81, had previously hosted its own famous supernova, SN 1993J, and although SN 1987A, located in the Large Magellanic Cloud, was much closer to Earth, SN 2014J remains the nearest Type Ia supernova observed since SN 1972E, making it a rare and extraordinary event in the modern exploration of galaxies. The Whirlpool Galaxy, also called Messier 51A or NGC 5194, is one of the most beautiful and well-known spiral galaxies in the night sky. It belongs to a type of galaxy called a grand design spiral, which means its spiral arms are easy to see and evenly shaped. At its centre is a strong Seyfert Type II core, an active area where a supermassive black hole is surrounded by glowing gas clouds. The Whirlpool Galaxy is located in the constellation Canes Venatici, also called the Hunting Dogs, and it is very important in astronomy because it was the first galaxy ever identified as a spiral. This galaxy is about 31 million light-years away from Earth, or roughly 9.5 megaparsecs. It spans nearly 77,000 light-years across, making it a little smaller than our Milky Way galaxy. The Whirlpool is not alone. It has a smaller companion galaxy called NGC 5195. The two are so close that they pull on each other with gravity. This dramatic cosmic dance can even be seen with simple binoculars, which makes the Whirlpool popular with amateur stargazers. Professional astronomers have spent many years studying this pair of galaxies. By observing the Whirlpool and its partner, scientists have learned more about how spiral arms form, how galaxies affect each other with gravity, and how collisions between galaxies shape the universe. Because the Whirlpool and its companion are close and easy to see, they have become one of the best-known examples of galaxies interacting. The story of its discovery goes back more than 200 years. On the 13th of October in 1773, a French astronomer named Charles Messier found the object while searching for things that could be mistaken for comets. He added it to his famous list of fuzzy sky objects and named it Messier 51. Later, in the 19th century, an Irish astronomer named William Parsons, the 3rd Earl of Ross, used a 72-inch reflecting telescope at Birr Castle to study it more closely. What he saw amazed him. The object had a spiral shape. This was the first time anyone had seen such a pattern in the sky, though at that time people did not know that spiral nebulae were actually whole galaxies like our own. It was only in the 20th century that American astronomer Edwin Hubble proved that these spiral nebulae were separate galaxies far beyond the Milky Way. He did this by finding a special kind of star called a Cepheid variable, which helped him measure their huge distances from Earth. With the rise of radio astronomy in the mid-20th century, scientists were able to make radio images of Messier 51 and confirm that the Whirlpool and its companion were really interacting galaxies. Today, when astronomers mention Messier 51, they often mean both galaxies together. To tell them apart, the larger galaxy is called M51A and the smaller one M51b. The Whirlpool is located deep in the constellation Canes Venatici. Observers often find it by starting at the bright star Alcaid, the star at the end of the Big Dipper's handle, and then moving about 3.5 degrees southwest. Because of its position in the sky, the Whirlpool never sets for people living north of the 43rd parallel, so it can be seen all year from northern places. It is best seen from November through May, when it rises high in the night sky. Even under a dark sky, the Whirlpool can be seen through ordinary binoculars as a faint patch of light. With a small telescope about 10 centimeters wide, its two parts can be seen as separate objects. With a 15 centimeter telescope, its spiral shape starts to appear faintly. Through larger telescopes of 30 centimeters or more, under very dark skies, the galaxy's spiral arms become bright and full of glowing regions where new stars are forming. Photos show far more detail than the human eye can see. Long exposure pictures reveal faint clouds and wisps of material stretching far beyond the visible spiral arms. In 1984, using a special fast detector called an image photon counting system on the Canada-France-Hawaii telescope at Mauna Kea, astronomers found that the Whirlpool's core actually has two parts, proof of its complex and active center. In January of 2005, the Hubble Space Telescope took one of the most detailed images ever of the Whirlpool galaxy. The image, made up of over 11,000 by almost 8,000 pixels, showed its sweeping arms in amazing clarity, with dark dust lanes, bright clusters of newborn stars and glowing gas clouds. The Whirlpool is between 23 and 31 million light-years from Earth. Studies done in 1991 suggest it is about 88% the size of our Milky Way, with a total mass of around 160 billion times that of the Sun. It is thought to be about 400 million years old, making it fairly young compared to some other galaxies. At its centre is a supermassive black hole. For a long time, astronomers thought this black hole was surrounded by a ring of dust. Later they found that the dust actually hides part of the black hole instead of circling it completely. From this active centre, two bright cones of ionized gas shoot into space, showing the galaxy's powerful and energetic core. The Whirlpool galaxy, also called Messier 51 or NGC 5194, is a grand and stunning spiral galaxy famous for its beautiful shape. It has two large, clearly marked spiral arms that curl clockwise, though one bends slightly off course. Astronomers think this unusual shape was caused by a close encounter with its smaller partner, NGC 5195. Research shows that this smaller galaxy may have passed through the main disk of the Whirlpool about 500 to 600 million years ago. During that event, NGC 5195 likely came from behind Messier 51, moved through its disk toward us, and then crossed it again between 50 and 100 million years ago. Today, we see it just behind the Whirlpool, caught in a slow and striking gravitational hold. This close encounter has created many amazing tidal features, huge streams of stars and gas pulled into space by their shared gravity. The largest is called the Northwest Plume, stretching about 43 kiloparsecs, or around 140,000 light-years, from the galaxy's center. This plume glows softly, suggesting it came from the whirlpool itself. Nearby are two slightly bluer plumes called the western plumes, which are more signs of the ongoing cosmic tug-of-war between these galaxies. In 2015, astronomers found two more features, called the northeast plume and the south plume. These discoveries confirmed that the interaction between Messier 51 and its partner happened more than once. Computer models showing multiple passes of NGC 5195 through the whirlpool match what scientists see today. At the heart of the whirlpool, stars are forming faster than usual. Astronomers say the rate of this star formation, the number of new stars compared to the gas available, is about 1%, similar to the Milky Way. However, this period of rapid star birth will not last forever. It is expected to continue for another 100 million years or so before slowing down. The spiral arms shine brightly with young stars, glowing with the light of new life spreading through the galaxy. Over the years, the whirlpool has had several bright supernova explosions, the powerful deaths of massive stars. The first recorded one appeared in 1994, called as N1994Y, and was a type-like supernova caused by a large star that had already lost most of its outer layers. Its brightness peaked at magnitude 12.91. Another explosion happened in June 2005, when an amateur astronomer named Wolfgang Kleur found SN 2005 CS, a Type II supernova that reached magnitude 14. Then, on the 31st of May in 2011, another Type II supernova called SN 2011 DH shone at magnitude 12.1. It had an unusually blue colour and showed signs of material moving outward very fast, suggesting the dying star was probably a yellow supergiant rather than a red or blue one. On the 22nd day of January in the year 2019, astronomers saw a fascinating and mysterious event in the Whirlpool Galaxy. A strange flash of light, called a supernova imposter, appeared and was named at 2019 ABN. At first, scientists thought it might be a normal exploding star, but later it turned out to be something even rarer, a luminous red nova. This kind of explosion happens when two stars crash and merge into one, creating a bright but short-lived glow that slowly fades away. The star system that caused this event had already been seen in infrared pictures taken by the Spitzer Space Telescope, but when astronomers looked for it in photos from the Hubble Space Telescope, they found nothing. The reason, they think, is that the star was hidden behind thick clouds of space dust, making it invisible in normal light. Researchers studying the Whirlpool Galaxy have also found that it is full of a rich mix of molecules, showing that it is not just a collection of stars but also a place with complex chemistry. Inside its wide spiral arms and bright centre, astronomers have found molecules like hydrogen cyanide, hydrogen isocyanide, aldehyde and diazonilium, substances also found in star-forming areas of our own Milky Way. However, some rare molecules like isocyanic acid and ethanol have been found only within about 1 kiloparsec, or roughly 3,000 light-years, from the galaxy's centre. This suggests that the heart of the Whirlpool Galaxy has special conditions, maybe stronger radiation or higher temperatures, that let these uncommon chemical compounds exist. In the month of September, in the year 2020, astronomers using the Chandra X-ray Observatory announced a discovery that surprised everyone, a possible planet outside our galaxy. This unusual candidate, called M51ULS1b, might be the very first known planet ever found outside the Milky Way. According to scientists, this world seems to orbit a strong X-ray source, a system where a huge B-type supergiant star is paired with a small dead remnant like a neutron star or a black hole. The planet itself is thought to be a little smaller than Saturn and orbits its star from a very large distance, tens of times the distance between Earth and the Sun. If confirmed, this would be an amazing discovery, showing that even in faraway galaxies, planets can form and survive in extreme conditions. Close to the Whirlpool Galaxy is its smaller companion, NGC 5195, also called Messier 51b. This tiny dwarf galaxy is locked in a cosmic dance with the larger Whirlpool Galaxy. The two have been interacting for millions of years, their gravity pulling and twisting their spiral arms into stunning shapes. Both galaxies are in the constellation called Canes Venatici, about 31 million light-years from Earth. Together, they form one of the most famous and well-studied pairs of galaxies in the universe, a breathtaking sight that has long fascinated astronomers and skywatchers alike. The Whirlpool Galaxy is also the brightest member of a small but important group of galaxies called the M51 group. This cluster includes the shining Sunflower Galaxy, also called Messier 63, along with NGC 5023 and NGC 5229. Scientists think this group may not be alone, but could be part of a much larger chain of galaxies stretching across space, possibly connecting to the M101 group and the NGC 5866 group. This huge structure reminds us that galaxies are rarely alone. They often form families, held together by gravity, creating beautiful patterns across the universe. The Pinwheel Galaxy, also called Messier 101, M101, or NGC 5457, is one of the most breathtaking spiral galaxies visible in the night sky. It lies at a staggering distance of about 21 million light-years from Earth, roughly 6.4 megaparsecs, nestled within the constellation of Ursa Major, the Great Bear. What makes this galaxy especially striking is that we see it face-on, looking directly at its wide, whirling disk of stars that spins gracefully counterclockwise through the darkness of space. The story of its discovery begins in the year 1781, when the French astronomer Pierre Méchain first spotted it. Later that year, he shared his observation with his friend and fellow astronomer Charles Messier. Messier confirmed its position and added it to his famous Messier catalogue, making it one of the final entries in that historic list. Centuries later, on the 28th of February in the year 2006, NASA and the European Space Agency revealed a stunningly detailed photograph of the Pinwheel Galaxy. This image was created by combining 51 separate exposures from the Hubble Space Telescope, along with additional pictures taken from Earth. At the time, it became the largest and most detailed image ever captured of a galaxy, showing the pinwheel in incredible clarity. When Pierre Méchain first observed it, he described the galaxy as a nebula without stars, very faint and rather large, about 6 to 7 arc-minutes across, between the left hand of Botez and the tail of the Great Bear. It is difficult to distinguish when one illuminates the grating wires. These poetic words remind us how mysterious and magical the universe appeared through the early telescopes of the 18th century. In 1784, the great astronomer William Herschel also studied the galaxy. Using his reflectors with focal lengths of 7, 10 and 20 feet, he noted a mottled kind of nebulosity and suggested that, with better instruments, it might one day be possible to see it resolved into individual stars. His early observations hinted at the true nature of galaxies long before astronomers fully understood them. Later, in the second half of the 19th century, Lord Rosse turned his enormous 72-inch Newtonian reflector telescope toward the same galaxy. He was the first to create detailed sketches of its stunning spiral structure, a crucial step in realizing that galaxies were not just faint clouds of gas, but enormous star systems in their own right. Today, the Pinwheel Galaxy is visible even through a pair of binoculars or a small telescope, although its delicate spiral arms reveal their full beauty only when viewed through a large telescope under very dark skies, ideally with a low-power eyepiece. The galaxy itself is colossal. Its disk stretches across approximately 252,000 light-years, nearly 3 times the width of our own Milky Way, which measures about 87,400 light-years across. Within its vast spiral, the Pinwheel Galaxy houses nearly 1 trillion stars, with a disk mass equivalent to roughly 100 billion times the mass of our Sun. At its centre lies a smaller, dense bulge containing about 3 billion solar masses, giving the galaxy a structure comparable to the mighty Andromeda Galaxy. One of the galaxy's most enchanting features is its abundance of glowing H2 regions, stellar nurseries where new stars are born. These regions form within enormous clouds of dense hydrogen gas that collapse under their own gravity. Young, hot stars then light up the surrounding gas with intense radiation, creating bright pink and red clouds that illuminate the sweeping spiral arms. In the year 1990, astronomers catalogued 1,264 of these glowing, star-forming regions in Messier 101. 3 of them, NGC 5461, NGC 5462, and NGC 5471, shine so brightly that they were given their own entries in the new general catalogue. Interestingly, the Pinwheel Galaxy is not perfectly symmetrical. Its spiral shape shows signs of being pulled and stretched by the gravity of nearby companion galaxies. These cosmic interactions compress hydrogen gas, sparking bursts of new star formation that shine even in ultraviolet light, invisible to the naked eye. In the year 2001, astronomers using the Chandra X-ray Observatory discovered an extraordinarily bright X-ray source within the galaxy, named P98. It was later called M101ULX1. This source is an ultra-luminous X-ray object, far brighter than any single star, though not as bright as an entire galaxy. Observations made by the Hubble Space Telescope and XMM Newton in 2005 revealed that it is an X-ray binary system consisting of two objects, one of which is likely a black hole pulling matter from a companion star. Remarkably, this black hole is estimated to have a mass only 20 to 30 times that of the Sun, yet it consumes matter at an incredibly fast rate, defying scientists' expectations. The Pinwheel Galaxy also contains around 150 globular clusters, a number similar to those found in our Milky Way. Surrounding it are 6 notable companion galaxies: NGC 5204, NGC 5474, NGC 5477, NGC 5585, UGC 8837, and UGC 9405. The gravitational pull between the pinwheel and these smaller neighbours may have helped shape its grand, sweeping spiral design. Together, these galaxies form the M101 group, a small, elegant family of galaxies drifting together through the vast cosmic ocean, bound by gravity and the slow passage of time. The Cartwheel Galaxy is an extraordinary ring-shaped lenticular galaxy located roughly 500 million light-years away in the constellation Sculptor. It stretches across a vast area with a diameter of about 188,200 light-years or 57.69 kiloparsecs, and it holds an estimated mass between 2.9 and 4.8 billion times that of our Sun. Its outer ring spins at an impressive speed of 217 kilometers per second. This remarkable galaxy was first spotted by the astronomer Fritz Zwicky in the year 1941. Zwicky himself described it as one of the most complicated structures awaiting its explanation based on stellar motion, highlighting just how unusual and puzzling the cartwheel appeared even to experts. The third reference catalogue of bright galaxies, also called RC3, measured the galaxy's diameter from its visible light at around 60.9 arcseconds. Using the distance derived from its redshift, this gives the same enormous size of 57.69 kiloparsecs. This makes the cartwheel slightly larger than our neighbouring Andromeda Galaxy, emphasising its grand scale. The Cartwheel Galaxy is the largest and most dominant member of a small group of galaxies that includes 4 physically related spiral galaxies. Its companions are labelled G1, a smaller irregular bluish galaxy resembling the Magellanic Clouds, G2, a yellow compact spiral with a trailing tidal tail, and G3, a more distant spiral often visible in wide-field images. Astronomers have observed one supernova in the Cartwheel Galaxy. This supernova, known as SN 2021 AFDX, was a Type II supernova with a magnitude of 18.796, discovered by the Atlas survey on the 23rd day of November in the year 2021. The structure of the Cartwheel Galaxy is highly complex and noticeably disturbed. It features 2 prominent rings, the outer ring, which glows brightly as a region of intense star formation caused by the compression of gas and dust, and the inner ring, which surrounds the galaxy's core. Encircling the inner ring is a band of dark dust that absorbs light. Connecting these rings are several optical arms, often referred to as spokes, which resemble the spokes of a cartwheel. Interestingly, observations show both radio and optical spokes, yet these 2 types do not perfectly overlap. The galaxy did not always look like this. Originally, it was likely a normal spiral galaxy, but around 200 to 300 million years ago, it underwent a dramatic head-on collision with a smaller companion galaxy. The impact sent a powerful gravitational shockwave rippling outward, sweeping up gas and dust and triggering an enormous burst of star formation in the expanding ring around the centre. This process created the galaxy's striking bluish ring, which shines brightly in images. Today, the cartwheel is slowly starting to regain a more typical spiral shape, with its arms spreading outward from the central core, the spokes seen in its current form. Alternative models suggest that rings and spokes in galaxies can form due to gravitational instabilities in both radial and spiral patterns, where matter clumps together along waves of instability. However, for the Cartwheel Galaxy, observation suggests this explanation does not fully account for its unusual structure. Among the 4 galaxies in the Cartwheel group, the 4th companion, G3, is linked to the Cartwheel by a stream of neutral hydrogen gas, known as an HI tail. This tail provides strong evidence that G3 was the bullet galaxy that collided with the Cartwheel, creating its current ring-like shape. G1 and G2, being closer to the Cartwheel, are unlikely to have caused the collision. The distance between the Cartwheel and G3 is roughly 287,000 light-years, or 88 kiloparsecs, which fits the timeline of the structure's formation about 300 million years ago. Hydrogen gas mapping is a key tool for astronomers to identify culprit galaxies and collisions, because hydrogen is the lightest and most abundant element in galaxies and is easily stripped away during gravitational interactions. Similar phenomena can be seen in galaxies like the Jellyfish Galaxy and the Comet Galaxy, where gas is pulled away by collisions or cluster interactions, forming tails and star-forming streams. The Cartwheel Galaxy is expected to gradually change over the next few hundred million years. Gas, dust, and stars that have not escaped will slowly fall back toward the centre, potentially allowing the galaxy to regain a more conventional spiral shape if its companions remain at a distance and no new collisions occur. The galaxy's unique structure has also led to bursts of extremely luminous star formation along its outer ring. Many of these massive stars eventually explode as supernovas, leaving behind neutron stars and black holes. Some of these black holes have companion stars and pull material from them, emitting intense X-rays and appearing as bright points along the galaxy's rim in X-ray images. The Cartwheel contains an unusually high number of these black hole binary systems, a direct result of the many massive stars formed during its dramatic starburst. Messier 81, also called NGC 3031 or Bode's Galaxy, is a stunning spiral galaxy located about 12 million light-years away in the constellation of Ursa Major, the Great Bear. It is a grand design spiral, which means its arms are clear and beautifully shaped, giving it a smooth and orderly look. Across its bright disk, the galaxy stretches about 29.5 kiloparsecs, or roughly 96,000 light-years, almost the same size as our Milky Way. Because Messier 81 is relatively close to our galaxy and shines brightly in the sky, it has become one of the most studied galaxies by astronomers worldwide. Its centre has a powerful and active core, home to a huge black hole weighing around 70 million times the mass of our Sun. This massive black hole makes the galaxy's centre glow with strong energy, which can be seen in many types of light. Both professional and amateur astronomers often observe Messier 81, not just because it is beautiful, but also because its brightness makes it easy to see even with small telescopes. In late February of 2022, scientists made an exciting discovery. They found that Messier 81 could be the source of a mysterious cosmic signal called a fast radio burst, specifically FRB 202000120E. These bursts are very strong flashes of radio waves that last only milliseconds, yet they release as much energy as the Sun does in several days. Messier 81 was first discovered on December 31, 1774, by the German astronomer Johann Elert Bode. Because of this, it is often called Bode's Galaxy. A few years later, in 1779, French astronomers Pierre Méchain and Charles Messier rediscovered it and added it to Messier's famous list of celestial objects. From Earth, the galaxy can be found about 10 degrees northwest of the bright star Alpha Ursae Majoris, also called Dubhe. It belongs to a small group of galaxies called the Messier 81 group, which contains several galaxies clustered in the same part of space. Because of its distance from Earth, Messier 81 cannot be seen with the naked eye except under very dark skies and by very skilled observers. However, with binoculars or a small telescope, both Messier 81 and its companion galaxy, Messier 82, can be seen together, a spectacular view for stargazers. To see details in its spiral arms, a telescope at least 8 inches, or about 20 centimeters, in diameter is usually needed. The best time to observe this galaxy is in April, when it is high in the night sky. Much of the galaxy's light in infrared comes from interstellar dust. This dust is mainly in the spiral arms, where new stars are forming. The hot, short-lived blue stars formed there shine strongly, heating the dust and making it glow in infrared light. Astronomers estimate that Messier 81 contains about 210 globular clusters, ancient, tightly packed groups of stars that orbit the galaxy's centre like sparkling jewels. Only one supernova has ever been seen in this galaxy. It was called Supernova 1993J, discovered on March 28, 1993, by the Spanish astronomer F. Garcia. At its brightest, it became one of the brightest supernovae of the 20th century, reaching a magnitude of about 10.7. Its behaviour was unusual. It started as a typical Type II supernova, showing strong hydrogen lines, but over time the hydrogen faded and helium became more visible. This made astronomers classify it as a Type IIb supernova, a stage between Type II and Type Ib explosions. These findings suggested that some Type Ib and Type Ic supernova might also come from the deaths of giant stars like Type II. The light from Supernova 1993J also helped scientists estimate Messier 81's distance at about 8.5 million light-years. The Central Bureau for Astronomical Telegrams still tracks new stars that appear in Messier 81, as well as in nearby galaxies like Messier 31 and Messier 33. At the galaxy's centre lies its huge supermassive black hole, about 70 million times heavier than the Sun. This black hole is active, surrounded by a glowing disk of falling material, and even shoots out a one-sided jet of fast particles into space. Some studies suggest there might be a smaller black hole orbiting the main one every 30 years, with a mass about 1/10 that of the larger black hole. Messier 81 is the biggest galaxy in its group, which has about 34 galaxies in total. Located about 12 million light-years from Earth, this group and our own local group, which includes the Milky Way, Andromeda and Triangulum, are considered close neighbours within the large Virgo supercluster. Interactions between Messier 81, Messier 82, and another nearby galaxy called NGC 3077 have caused dramatic effects. Their strong gravity has pulled huge amounts of hydrogen gas from each galaxy, creating long glowing filaments in space. These interactions have also pushed gas toward the centres of Messier 82 and NGC 3077, triggering intense waves of star formation called starbursts. Finally, by observing special stars called Cepheid variables, stars whose brightness changes in regular cycles, astronomers using the Hubble Space Telescope have measured Messier 81's distance to be about 11.8 million light-years. This accurate measurement was made possible thanks to the pioneering work of Henrietta Swan-Leavitt, who first found the link between a Cepheid star's brightness and its pulsation cycle. Centaurus A, also known by its catalogue names NGC 5128 and Caldwell 77, is an amazing and mysterious galaxy that lies deep in the constellation of Centaurus. It was first found in the year 1826 by the Scottish astronomer James Dunlop, who observed it from his home in Parramatta, New South Wales, Australia. Since then, Centaurus A has become one of the most studied and fascinating galaxies in the southern sky. Astronomers have long argued about its true type, whether it should be called a lenticular galaxy or a giant elliptical one. Its distance from Earth is thought to be between 11 and 13 million light-years, making it the closest known radio galaxy and also the nearest object of a kind called a BL-Lac object. Because of this, its active centre, the very energetic region in the middle, has been studied a lot by scientists. It shines as the fifth brightest galaxy visible from Earth, which makes it popular with amateur astronomers, though it can only be seen clearly from the southern hemisphere and lower northern latitudes. At the centre of Centaurus A is a huge supermassive black hole, with a mass about 55 million times bigger than our Sun. From this giant core, a stream of particles shoots out at speeds close to half the speed of light, giving off strong energy in X-rays and radio waves. Observations over 10 years have shown that the inner parts of this stream move at incredible speeds. While farther away, it crashes into clouds of gas, creating bursts of X-rays and making highly energetic particles. The X-ray stream alone stretches thousands of light-years, while the radio stream goes even farther, over 1 million light-years, making it one of the largest and most impressive structures ever seen in a nearby galaxy. Centaurus A is also known as one of the closest big starburst galaxies going through a strong wave of star formation. Scientists think this activity started when two galaxies collided, a large elliptical galaxy and a smaller spiral one. Over time, these two galaxies began to merge, creating huge clouds of dust and gas and triggering the birth of countless new stars. Such collisions are common between spiral galaxies, but interactions between a spiral and an elliptical galaxy are much rarer and not yet fully understood, which is why Centaurus A is so important to study. The story of its discovery and study covers nearly 200 years. After Dunlop first saw it on the 29th of April in 1826, the famous astronomer John Herschel described it in 1847 as looking like two glowing halves of a cloud split by a dark band of dust. Nearly a century later, in 1949, John Bolton, Bruce Slee and Gordon Stanley found it was one of the first galaxies known to send out strong radio waves. In 1954, Walter Baade and Rudolf Minkowski suggested that its strange shape came from a galactic collision, an idea later confirmed by more research. Over the years, many important discoveries followed. In 1970, scientists detected X-rays from the galaxy using a small rocket. In the mid-1970s, gamma rays were seen for the first time. In 1979, the Einstein Observatory showed an X-ray stream coming from the center, and 10 years later, the Hubble Space Telescope found young blue stars forming along the dark dust band. In 1999, the Chandra X-ray Observatory found more than 200 new bright points of X-ray light, while in 2006 the Spitzer Space Telescope showed a fascinating parallelogram-shaped dust structure glowing in infrared light. In 2009, astronomers at the HESS Observatory in Namibia detected strong gamma rays from Centaurus A, and the next year, the Pierre Auger Observatory confirmed that it also sends out some of the highest energy cosmic rays ever recorded. In 2016, new data from the Chandra and XMM Newton space telescopes showed strange bursts of energy that may be linked to a new kind of black hole or a medium-sized black hole. More recently, the James Webb Space Telescope, using its MIRI-MIRS instrument, looked at the central region of Centaurus A in incredible detail. These high-resolution images showed fast-moving clouds of charged gas streaming outward at speeds over 1,000 kilometers per second. These flows seem to come from a tiny area only about 6 parsecs wide, roughly 20 light-years, where the galaxy's powerful stream hits the surrounding material, creating a busy and turbulent environment filled with shocks and radiation. From Earth, Centaurus. He looks like an elliptical galaxy, crossed by a thick dark band of dust that almost splits it in two. This striking look led astronomer Halton Arp to include it in his Atlas of Peculiar Galaxies in 1966 as a prime example of a disturbed galaxy. Its bright central bulge is mostly older, reddish stars, while its dusty disk still makes new stars. Over 100 regions of star formation have been found there. 2 supernovae have also been seen in this galaxy. The first, called Supernova 1986G, was discovered by Robert Evans on the 3rd of May in 1986. It was a type Ia supernova, formed when a white dwarf star collected too much matter from its companion and exploded in a bright thermonuclear blast. This event helped astronomers see that not all type Ia supernovae act exactly the same. The second, called Supernova 2016 ADJ, was discovered in February 2016 and was first thought to be a Type II supernova. Later studies showed it more closely matched a Type Ib explosion, caused by the collapse of a huge star that had lost its outer hydrogen layer. Another rare event, a luminous red nova called 2020 NQ, was seen on the 27th of June in 2020, marking the merging of 2 stars in the galaxy. Even more recently, 2 new novae, a 2024 AEQL and a 2025 NOC, were found in December 2024 and June 2025. The distance to Centaurus A has been measured using several methods, such as observing Cepheid variable stars and Mira variables, and most estimates now put it around 3 to 4 million parsecs, or about 12 million light-years. This makes it not only one of the closest and brightest galaxies nearby, but also one of the most complex and active. A huge cosmic lab where astronomers keep learning how galaxies collide, change, and make new stars across the universe. Centaurus A sits at the center of one of the 2 main subgroups in the Centaurus A Messier 83 group. a cluster of nearby galaxies held together by gravity. The other subgroup centres on Messier 83, also called the Southern Pinwheel Galaxy. Astronomers sometimes call these two subgroups one large group, while others treat them as two separate groups. In reality, the galaxies around Centaurus A and those around Messier 83 are physically very close, and both seem to move together through space, showing little motion relative to each other. Altogether, the Centaurus A Messier 83 group is part of a much bigger collection of galaxies called the Virgo supercluster, the vast galactic region that also includes our Milky Way. Like many big galaxies, Centaurus A is surrounded by hundreds of globular clusters, ancient, tightly packed groups of stars that orbit its edges. Some of these may not be ordinary clusters, but the remains of small galaxies torn apart by Centaurus A's strong gravity. The most notable example is an object called VHH 8101, which is thought to hold a central black hole about 800,000 times more massive than the Sun, a clue that it was once the centre of a much bigger galaxy. In July 2021, the Event Horizon Telescope, the same international project that captured the first image of a black hole, released a detailed picture of Centaurus A. This showed a bright stream of material shooting from the supermassive black hole at the centre, a dramatic feature that helps astronomers understand how such black holes shape the galaxies around them. Centaurus A lies about 4 degrees north of Omega Centauri, a stunning globular cluster visible to the naked eye. Because Centaurus A is bright and covers a fairly large area of the sky, it is popular with amateur astronomers. Even small telescopes or large binoculars show its bright central bulge and the thick, dark lane of dust across it. With bigger telescopes, more details appear: faint arms, glowing clouds, and delicate shapes shaped by cosmic forces. In very clear and dark skies, some observers have even said Centaurus A can be seen without a telescope, appearing as a faint smudge in the constellation of Centaurus, a ghostly reminder of the vast universe beyond our Milky Way. The Triangulum Galaxy is a beautiful spiral-shaped galaxy that sits about 2,730,000 light-years from Earth, inside a small constellation called Triangulum. Astronomers often call it Messier 33 or NGC 598. When measured across its visible size, called its D25 isophotal diameter, it stretches about 18.74 kiloparsecs, or roughly 61,100 light-years wide. This makes it the third largest galaxy in our local group of galaxies, after the huge Andromeda Galaxy and our own Milky Way. Even though it is quite large, the Triangulum Galaxy is actually the second smallest spiral galaxy in the local group, just bigger than the Large Magellanic Cloud, which is a smaller type of spiral galaxy called a Magellanic-type galaxy. Many astronomers think Triangulum might be a companion or satellite of Andromeda, or maybe it is now moving back toward Andromeda after once being closer to it. This idea comes from the fact that both galaxies move at similar speeds and are close to each other in the sky. Interestingly, Triangulum also has what is called an H2 nucleus, a region full of charged hydrogen gas where new stars are forming. The galaxy's name comes from its constellation Triangulum, which means triangle. Some books and websites also call it the Pinwheel Galaxy, although that name is more correctly used for another galaxy, Messier 101, in the constellation Ursa Major. Still, the nickname Pinwheel Galaxy sometimes appears in telescope guides and astronomy sites, showing how names can easily get mixed up in space. Under very clear and dark skies, far away from city lights, the Triangulum Galaxy can sometimes be seen without a telescope. For those lucky enough to see it, this faint, cloudy patch of light is the farthest object visible to the human eye, almost 1.5 times farther away than the Andromeda Galaxy. Unlike stars, which look like tiny points of light, Triangulum appears as a soft, hazy glow because of its wide and spread-out shape. How well it can be seen depends on how dark and clear the sky is. In deep countryside areas with no city lights, some people can see it directly, while others might only notice it by looking slightly to the side, a trick called averted vision. Because of this, the galaxy is often used as a guide on the Bortle dark sky scale, which measures how dark the night sky is. Although its total apparent brightness, its so-called V magnitude, is about 5.72, its actual visual brightness is closer to 6.6. This means only people with very sharp eyesight and excellent sky conditions can see it without a telescope. For most people, Even under perfect skies, it remains too faint to see with the naked eye. The Triangulum Galaxy has a long and interesting discovery history. It was probably first noticed before the year 1654 by the Italian astronomer Giovanni Battista Hodierna, who described it as a cloudy spot near the constellation Triangulum. Over a century later, on the night between August 25th and 26th in 1764, the French astronomer Charles Messier found it again by himself. He listed it as the 33rd object in his famous catalogue of nebulae and star clusters, hence its name, Messier 33. Later, the great astronomer William Herschel added it to his own catalogue on September 11th, 1784, calling it HV17. Herschel also studied several glowing gas clouds inside Triangulum, called H2 regions, where young stars are forming. One of these, called NGC 604, lies to the northeast of the galaxy's bright centre and is one of the largest H2 regions known. It stretches about 1,500 light-years across, an enormous area that shines with light similar to the famous Orion Nebula. Herschel also noted 3 smaller nearby H2 regions, listed as NGC 588, 592, and 595. In the mid-19th century, around 1850, Lord Rosse was among the first to see Triangulum as a spiral nebula, noticing its graceful swirling pattern. Then, in the early 1920s, astronomers John Charles Duncan and Max Wolf discovered stars inside it whose brightness changes over time, called variable stars. In 1926, Edwin Hubble studied 35 of these stars, called Cepheid variables, and used them to measure how far Triangulum is. His work helped prove that spiral nebulae like Triangulum were not just gas clouds inside our Milky Way, but were actually whole galaxies of their own, huge systems filled with stars. The Triangulum Galaxy is thought to contain about 40 billion stars, much fewer than the Milky Way's 400 billion, and tiny compared to Andromeda's trillion stars. Its disk holds between 3 and 6 billion times the mass of our Sun, while its gas alone makes up about 3.2 billion solar masses. Altogether, the galaxy's normal matter, called baryonic matter, may weigh about 10 billion solar masses, but when dark matter is included, the total mass rises to nearly 50 billion solar masses within about 55,000 light-years from its centre. Astronomers have worked hard to measure exactly how far Triangulum is from us. Most estimates place it between 2,380,000 and 3,070,000 light-years away, with most experts agreeing on an average distance of about 2,770,000 light-years. This makes it slightly farther than Andromeda. Triangulum is also about 750,000 light-years away from Andromeda, which supports the idea that the two galaxies might be connected by gravity. In 2006, astronomers found a pair of stars in Triangulum that regularly pass in front of each other, called an eclipsing binary system. By studying how their light changes as they move, scientists could find their sizes, brightness, and exact distance, about 3,070,000 light-years from Earth. This confirmed earlier guesses and became one of the most accurate distance measurements ever made for a nearby galaxy. The Triangulum Galaxy also gives off a special kind of radiation called a water maser signal, which helps astronomers track its movement through space. In 2005, scientists using this method found that Triangulum is moving toward the Andromeda Galaxy at a speed of around 190 km per second. This supports the idea that it might be orbiting Andromeda or moving back toward it after a close meeting long ago. Further studies in the early 21st century showed a faint stream of hydrogen gas connecting the two galaxies, hinting that they may have interacted in the past. Later observations confirmed this link, showing that their small distance, less than 300 kiloparsecs, or about 1 million light-years, makes such an interaction very likely. Close to Triangulum lies a small galaxy called the Pisces Dwarf, or LGS-3. It sits about 2,022,000 light-years from the Sun, and is roughly halfway between Andromeda and Triangulum. Since it is about 913,000 light-years from each, it could be a small companion of either one. It holds around 26 million solar masses of material and has a centre about 483 light-years wide. Another faint object, called Pisces 7 or Triangulum 3, may also be a small companion of the Triangulum Galaxy. In the updated Hubble Sandage system of galaxy types, made by the French astronomer Gérard de Vaucouleurs, the Triangulum Galaxy is labelled as type SAS.CD. Each part of this code tells astronomers something about its shape. The letter S means the galaxy has a flat disc-like shape with gas and dust spiraling out from its bright center, the classic look of a spiral galaxy. The letter A shows that its center does not have a bar running through it, unlike galaxies of the SB type, which do have one. The S, introduced by the American astronomer Alan Sandage, means that the spiral arms start directly from the center rather than from a surrounding ring. Lastly, the CD at the end shows that the galaxy's arms are loosely wound and open, giving it a delicate and graceful look. The Triangulum galaxy sits tilted at about 54 degrees from our view on Earth. This tilt is helpful because it lets astronomers see its disk and spiral arms clearly, without much blocking from its clouds of gas and dust. When scientists carefully mapped the shape of the galaxy's disk, they noticed that it bends or warps slightly outward, stretching to about 8 kiloparsecs from the center, roughly 26,000 light-years. Although there may be a faint halo of stars and gas around it, the Triangulum galaxy does not seem to have a thick, bulging center like many other spiral galaxies. Interestingly, the Triangulum galaxy lives quite a lonely life. It shows no signs of recently crashing into or joining with other galaxies, nor does it show faint trails of stars or small companion galaxies like those around the Milky Way. It is officially called an unbarred spiral galaxy, yet closer studies suggest that a faint, short, bar-shaped feature might exist near its center. This weak structure stretches out to about 0.8 kiloparsecs, a little over 2,500 light-years, showing that even in an unbarred galaxy, some light bar patterns can still appear. In the galaxy's central area, which spans about 4 arc-minutes across the sky, something fascinating is happening. Here, clouds of atomic gas are turning into molecular gas, giving off strong carbon monoxide signals, a clear sign that molecules are actively forming. This happens as huge molecular clouds grow from the gas and dust that fill the space between stars. Beyond this central area, the same process continues but at a much slower speed. Altogether, about 1/10 of all the gas in the Triangulum galaxy exists as molecular gas, the main material needed for new stars to form. Star formation in Triangulum follows a simple rule: the thicker the gas in an area, the faster new stars are born there. In fact, the rate of star birth per area is higher here than in the nearby Andromeda galaxy. For every square parsec of its disk, Triangulum creates stars at an average rate of about 3.4 solar masses per billion years, compared to only about 0.74 in Andromeda. Altogether, the entire galaxy forms about 0.45 solar masses of new stars each year, though astronomers are still unsure whether this rate is staying the same or slowly dropping over time. When scientists studied the chemical makeup of the Triangulum galaxy, they found that it seems to have 2 main parts, each with a different story. The inner disk, stretching about 30,000 light-years, or 9 kiloparsecs, from the center, shows a usual pattern in its chemical mix. The amount of heavy elements slowly drops as you move outward. Beyond this area, stretching out to about 82,000 light-years, or 25 kiloparsecs, this pattern becomes much flatter. This shows that the outer disk and halo have had a different history of star birth than the inner parts. Many astronomers think this fits with the inside-out model of galaxy growth. In this process, a galaxy first forms its dense inner parts, where stars quickly use up much of the gas. Over time, new gas is slowly pulled in from nearby space, gathering in the outer areas and starting later waves of star birth. Because of this, the stars farther from the center are usually younger than those near the core, showing a calm but beautiful story of how the Triangulum galaxy has slowly grown outward over time. By the year 2007, astronomers using the powerful infrared vision of the Spitzer Space Telescope had recorded a total of 515 separate sources of 24 micrometer radiation shining inside the Triangulum galaxy. These glowing spots show areas full of dust and gas, often heated by nearby young stars. The brightest ones are found in the center of the galaxy and spread gracefully along its spiral arms, where new stars are forming in large numbers. Many of these glowing clouds are linked to large H2 regions, huge clouds of charged hydrogen where stars are actively forming. Some of the most amazing of these are 4 giant regions called NGC 588, NGC 592, NGC 595, and NGC 604. Each of these holds massive molecular clouds weighing between 120,000 and 400,000 times the mass of our Sun. The largest and brightest of them, NGC 604, seems to have gone through a strong burst of starbirth about 3 million years ago. This great nebula shines with a brightness 45 million times greater than the Sun, making it the second brightest H2 region in the whole local group of galaxies. Other well-known star-forming nebulae in the Triangulum Galaxy include IC 132, IC 133, and IK 53. The galaxy's northern spiral arm holds 4 large H2 regions, while its southern arm is full of groups of young, bright, and very hot stars. The Triangulum Galaxy also sees the occasional huge explosion of dying stars. Astronomers believe that, on average, one supernova happens about every 147 years, equal to about 0.06 type Ya and 0.62 type Eb or type 2 explosions per century. By the year 2008, scientists had found about 100 supernova remains across the galaxy, with most of them in its southern half. This uneven pattern can also be seen in other things, like clouds of neutral and charged hydrogen and groups of massive O-type stars. The centre of these features seems to be slightly shifted, about 2 arc-minutes, toward the southwest. Because the Triangulum Galaxy is one of our closest galactic neighbours, the Central Bureau for Astronomical Telegrams continues to watch it closely for new novae, along with the Andromeda Galaxy and Messier 81. Astronomers have also found about 54 globular clusters orbiting inside the Triangulum Galaxy, though the real number could be as high as 122 or more. Interestingly, these clusters seem to be several billion years younger than those in our Milky Way, showing that the galaxy has kept forming new clusters quite recently. In fact, over the last 100 million years, the rate of cluster formation seems to have gone up, probably because of a flow of gas toward the galaxy's centre. The ultraviolet light from its massive stars matches that of similar stars in the Large Magellanic Cloud, showing that the Triangulum Galaxy is still a lively and active place where stars are being born. In the same year, 2007, astronomers made another exciting discovery using data from the Chandra X-ray Observatory, a black hole about 15.7 times the mass of our Sun, named M33X7. This stellar black hole orbits a companion star, passing right in front of it every 3.5 days, creating a regular eclipse. It remains one of the biggest stellar mass black holes ever found. Unlike our Milky Way or the Grand Andromeda Galaxy, the Triangulum Galaxy stands out in a very unusual way. It does not seem to have a supermassive black hole hiding at its centre. In most large galaxies, these giant black holes sit deep in the middle, surrounded by a bright, bulging cluster of stars. But the Triangulum Galaxy is different. It is a true disk galaxy, smooth, flat, and graceful, without that central bulge where such enormous black holes usually form. This may explain why its core appears surprisingly calm and less intense compared to the blazing centres of larger galaxies. Careful studies have shown that the Triangulum Galaxy is not completely alone in space. It is delicately connected to the Andromeda Galaxy by faint, ghostly bridges made of neutral hydrogen gas and by thin streams of wandering stars. These cosmic threads are almost invisible, but they tell an amazing story. They hint that long ago, perhaps between 2 and 8 billion years in the past, the two galaxies may have passed close to each other, like dancers moving through the same space before drifting apart again. Astronomers believe that this ancient meeting was just a preview, and that in about 2.5 billion years the two galaxies will come together once more in a far bigger and more dramatic encounter. By the year 2009, scientists were still unsure what the final fate of the Triangulum Galaxy would be. Some believe that Andromeda's huge gravity would eventually tear it apart and absorb it, using its rich stores of hydrogen gas to create new stars. Others thought that Triangulum might slowly burn through its remaining gas, grow dimmer over time, and fade into a quiet, starless shadow of what it once was. There were even bolder ideas, that Triangulum might someday join the massive collision between the Milky Way and Andromeda, merging with them to form one vast new galaxy. A few scientists even guessed that it could take a completely different path, perhaps colliding with the Milky Way first, or being thrown out of our local group altogether, sent adrift into the empty darkness between galaxy clusters. But in the year 2019, a new discovery changed everything. Using the precise measurements gathered by the Gaia Space Observatory, astronomers found fresh evidence about Triangulum's movement. These data showed that Triangulum is not gently orbiting around Andromeda as once thought. Instead, it is moving inward toward it. For the very first time. If this is true, we are seeing the start of an amazing journey, the beginning of Triangulum's long and winding path toward a cosmic reunion with its old neighbour Andromeda, a dance that will reshape both galaxies across the ages to come. The Antennae Galaxies, also known as NGC 4038 and NGC 4039, or Caldwell 60 and Caldwell 61, are a breathtaking pair of galaxies locked in a cosmic dance in the constellation of Corvus, the Crow. These two galaxies are in the middle of an extraordinary phase called a starburst, where clouds of gas and dust crash and mix, tangled with magnetic fields, creating new stars at a spectacularly fast pace. The famous astronomer William Herschel first spotted them in the year 1785. These galaxies are currently colliding, a process that is still unfolding. In the night sky, they can be found just 1/4 of a degree north of the star 31 Craterus, and a little over 3 degrees southwest of the star Gamma Corvi. They belong to a small galaxy group known as the NGC 4038 group, which includes 5 other galaxies. The Antennae Galaxies earned their nickname because of the 2 long graceful tails of stars, gas and dust that stretch outward from them, formed by the immense force of the collision, resembling the antennae of an insect. At their centres, the 2 galaxies are slowly merging to create a single, enormous galaxy. Most galaxies are thought to experience at least one major collision during their lifetimes. In fact, the Milky Way may eventually have a similar fate, with roughly a 50% chance of colliding with our nearest giant neighbour, the Andromeda Galaxy. The study of these merging galaxies, particularly their antennae, has helped astronomers develop a model called the Tumor sequence, which describes how galaxies evolve through collisions and mergers. Within the Antennae Galaxies, astronomers have discovered a relatively young collection of massive globular clusters, likely born from the violent encounter between the 2 galaxies. This is striking because most globular clusters are ancient, around 12 billion years old. These newly formed clusters probably came from shock waves created during the collision, which compressed enormous clouds of gas and dust. The densest parts of these clouds became the cradles for new star clusters. NGC 4038 is home to many Cepheid variable stars, with about 53 known so far. These galaxies are generally thought to be located around 20 megaparsecs, or roughly 70 million light-years, from Earth. However, a study in the year 2008 suggested they might be closer, at about 13.3 megaparsecs, or 43.4 million light-years. Later research questioned this, pointing out errors in identifying the tip of the red giant stars used for measurement. A more widely accepted estimate, based on a combination of observations including a Type 1a supernova in the southern tail, places the antennae at about 22 megaparsecs, or nearly 72 million light-years away. About 1,200,000,000 years ago, the 2 galaxies were completely separate. NGC 4038 was a barred spiral galaxy, while NGC 4039 was a regular spiral galaxy. Around 900 million years ago, they began moving toward each other, appearing somewhat like the galaxies NGC 227 and IC 216. 600 million years ago, they passed through one another, resembling the famous mice galaxies. 300 million years ago, stars started to be flung outward from both galaxies. Today, these streams of stars stretch far beyond their original homes, creating the distinctive antennae shape that gives the galaxies their name. In roughly 400 million years, the central cores of the 2 galaxies are expected to collide completely, forming a single, enormous nucleus surrounded by stars, gas and dust. Studies and simulations of colliding galaxies, such as those conducted by Ala Tumri, suggest that the Antennae Galaxies will eventually settle into an elliptical shape, becoming a smooth, rounded galaxy. Observations from the Chandra X-ray Observatory have revealed clouds within the Antennae Galaxies rich in elements like neon, magnesium and silicon. These heavy elements are essential for forming planets that could potentially support life, at least as we understand it. The clouds in the antennae contain 16 times as much magnesium and 24 times as much silicon as our Sun, showing that these galaxies are producing the raw materials needed for future worlds. A dwarf galaxy is a small, faint group of stars, much smaller than our Milky Way galaxy. While the Milky Way has somewhere between 200 billion and 400 billion stars, a dwarf galaxy may have as few as 1,000 to only a few billion. One well-known example is the Large Magellanic Cloud, a nearby companion of the Milky Way that has more than 30 billion stars. Some astronomers still argue whether it should be called a true dwarf galaxy or a normal galaxy on its own, because it is in between both types in size and brightness. The birth and behaviour of dwarf galaxies are strongly affected by the pull of much larger galaxies near them. Astronomers have found that there are many types of dwarf galaxies, and they are usually grouped based on their shapes and the stuff they contain. Some are smooth and round, while others look uneven and scattered. One common idea says that galaxies, including dwarf ones, formed together with large amounts of mysterious dark matter or from clouds of gas that already had small amounts of heavy elements, which astronomers call metals. But a discovery by NASA's Galaxy Evolution Explorer spacecraft showed something different. Some dwarf galaxies are actually forming from gases that have very little metal in them. These newly forming galaxies were found inside a huge ring of hydrogen and helium called the Leo ring, which goes around two very large galaxies in the constellation of Leo. Because they are so small and light, dwarf galaxies often fall victim to the strong gravity of nearby spiral galaxies. As they are pulled closer, their stars can be stretched into long glowing trails called stellar streams, and over time they may be completely torn apart and absorbed, joining with their bigger neighbours. In our own local area of space, called the Local Group, there are many dwarf galaxies orbiting bigger ones like the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. In the year 2007, astronomers suggested that some of these dwarfs may have been formed from violent gravitational forces, called tidal forces, that happened when the Milky Way and Andromeda were still forming. These so-called tidal dwarf galaxies appear when two galaxies collide, pulling streams of stars, gas, and even invisible dark matter away from each other to make new, smaller galaxies. Some dwarf galaxies may be much older than we thought. A study published in the year 2018 suggested that a few local dwarf galaxies were formed very early in the history of the universe, during the mysterious Dark Ages, less than 1 billion years after the Big Bang. Today, astronomers have found more than 20 dwarf galaxies orbiting the Milky Way. One interesting discovery is that the giant globular star cluster called Omega Centauri may actually be the leftover core of a dwarf galaxy that was swallowed by the Milky Way long ago. At its centre, scientists think, is a hidden black hole. Among the many types of dwarf galaxies, one very noticeable type is the Blue Compact Dwarf Galaxy, often called Blue Compact Dwarf or BCD Galaxy. These are small galaxies filled with large clusters of young, massive and very hot stars. Because these stars shine so brightly in blue and white light, the whole galaxy looks blue. Blue Compact Dwarf galaxies often have uneven shapes because they are made of separate clusters instead of a single smooth disk. They are also very active, constantly burning gas to make new stars, which causes big bursts of energy and fast changes. Over time, as their gas cools and new stars are born, their look slowly changes. Nearby examples include NGC 1705, NGC 2915, NGC 3353, and UJ 281. Another type of small galaxy is called ultra-faint dwarf galaxies, or ultra-faint dwarfs. These are the dimmest galaxies known in the whole universe, with only a few hundred to about 100,000 stars. Though they look a bit like globular clusters, they are very different inside. Ultra-faint dwarfs are full of dark matter and spread out over a much larger space. They were first discovered in the year 2005, thanks to detailed digital sky surveys like the Sloan Digital Sky Survey. Because ultra-faint dwarfs are mostly made of dark matter, astronomers think they may hold important clues about how the universe looked shortly after it began. All the ones found so far seem to be very old, forming only a few million years after the Big Bang, long before the universe's first light appeared during the epoch of reionization. Some scientists have suggested that there might be a younger group of ultra-faint dwarfs that formed much later, but none have been seen yet. There is also a special group of dwarf galaxies called ultra-compact dwarfs, or ultra-compact dwarfs. These were found in the early years of the 21st century and are among the densest star systems known. A typical ultra-compact dwarf is only about 200 light-years across, but can hold nearly 100 million stars packed closely together. Many astronomers think these tiny galaxies are actually the cores of larger dwarf galaxies, whose outer stars and gas were stripped away as they moved through big galaxy clusters. Ultra-compact dwarfs have been found in the Virgo cluster, the Fornax cluster, Abell 1689, and the Coma cluster. One famous example, M60 Ultra-Compact Dwarf 1, is about 54 million light-years away. It has around 200 million times the mass of our Sun packed into a space just 160 light-years wide. The stars in its centre are 25 times denser than those in the part of the Milky Way where our Sun is. Another, called M59 Ultra-Compact Dwarf 3, is similar in size but shines about 40% more brightly, making it the second densest galaxy known. Some ultra-compact dwarfs in the Virgo cluster even seem to have huge black holes at their centres, making up more than 1/10 of their total mass, a sign that these small galaxies may once have been much bigger cosmic structures long ago.